Hi there, we're in the lab with your mate JJ. Today is New Book Teardown Day. We're going to be tearing down a new book. My silly job title for today is Operation Manager, to them, Operation Manager. And the operation I'll be managing is a look into this book. It's called Basic Circuit Analysis. It's from the Shorm's Outlines series, 700 Fully Solved Problems. So we're going to be having a look at the book. Before we do, I thought I'd take you over to the Amazon website and just read about the book itself. And there'll be a link in the show notes if you're interested yourself. So let's jump over to the computer and have a look at the Amazon page for the book. All right. Well, here we are on the computer, and this is the web page for the book. It's called Shorm's Outline of Basic Circuit Analysis, second edition. The ideal review for your basic circuit analysis course. More than 40 million students have trusted Shorm's outlines for their expert knowledge and helpful solve problems. Written by a renowned expert in their respective fields, Shorm's outlines cover everything from math to science, nursing to language. The main feature of all these books is to solve problems. Step by step, authors walk readers through coming up with solutions to exercises in their topic of choice. 700 solved problems. Outline format supplies a concise guide to the standard college course in basic circuits. Clear, concise explanations of all electric circuit concepts, appropriate for the following courses: basic circuit analysis, electrical circuits, electrical engineering circuit analysis, introduction to circuit analysis, AC and DC circuits. Supports and supplements the basic best-selling textbooks in circuits. Easily understood review of basic circuit analysis. Supports all the major textbooks for basic circuit analysis courses. So that's what we're looking at. Looks like you can get some other Shorm's outlines as well. You can get basic electricity and outline of electric circuits. There you go. So yeah, those look interesting. I might follow up with those. But the first thing to do is to get through basic circuit analysis. So let's jump over to the bench and have a look at what's in this thing. All right, well, here we are on the bench, and this is our book. Shorm's Outlines, Problem Solved, Basic Circuit Analysis, second edition, 700 fully solved problems, concise explanations of all course concepts, information on capacitance, capacitor construction, energy storage, magnetic flux, inductance, inductor construction, sine and cosine waves, and resistor sinusoidal responses. Used with these courses: basic circuit analysis, electrical circuits, electrical engineering circuit analysis, introduction to circuit analysis, and AC and DC circuits. Written by John O'Malley, PhD. And on the back, what does it have to say? Tough test questions, limited missed lectures, not enough time. Fortunately, there's Shorm's. More than 40 million students have trusted Shorm's to help them succeed in the classroom and on exams. Shorm's is the key to faster learning and higher grades in every subject. Each outline presents all the essential course information in an easy-to-follow, topic-by-topic format. You also get hundreds of examples, solve problems, and practice exercise to test your skills. This Shorm's outline gives you 700 fully solved problems, an easy-to-understand review of basic circuit analysis, support for all the major textbooks for basic circuit analysis courses. Fully compatible with your classroom text, Shorm's highlights all the important facts you need to know. Use Shorm's to shorten your study time and get your best test scores. Shorm's outline, problem solve. Learn more, do more. McGraw-Hill, mhprofessional.com. There you go. This book sells for $22 US. Ripper. Well, let's have a look what's in here. So, when was it published? 2011. Cool. Dedicated to the loving memory of my brother Norman Joseph O'Malley, lawyer, engineer, and mentor. Here is the preface from John R. O'Malley. Studying from this book will help both electrical technology and electrical engineering students learn circuit analysis with, it is hoped, less effort and more understanding. Since this book begins with the analysis of DC resistive circuits and continues to that of AC circuits, as do the popular circuit analysis textbooks, a student can, from the start, use this book as a supplement to a circuit analysis textbook. The reader does not need a knowledge of differential or integral calculus, even though this book has derivatives in the chapters on capacitors, inductors, and transformers, as is required for the voltage-current relations. The few problems with derivatives have clear physical explanations of them, and there is not a single integral anywhere in the book. Despite its lack of higher mathematics, the book can be very useful to an electrical engineering reader, since most material in an electrical engineering circuit analysis course requires only a knowledge of algebra. Where there are different definitions in the electrical technology and engineering fields, as for capacitive reactances, phases, and reactive power, the reader is cautioned and the various definitions are explained. One of the special features of this book is the presentation of PSpice, which is a computer circuit analysis or simulation program that is suitable for use on personal computers, PCs. PSpice is similar to SPICE, which has become the standard for analog circuit simulation for the entire electronics industry. Another special feature is the presentation of operational amplifier or op-amp circuits. Both of these topics are new to this second edition. Another topic that has been added is the use of advanced scientific calculators to solve the simultaneous equations that arise in circuit analyses. Although this use requires placing the equations in matrix form, absolutely no knowledge of matrix algebra is required. Finally, there are many more problems involving circuits that contain dependent sources than there were in the first edition. I wish to thank Dr. R.L. Sullivan, who, while I was writing this second edition, was chairman of the Department of Electrical Engineering at the University of Florida. He nurtured an environment that made it conducive to the writing of books. Thanks are also due to my wife, Louis Ann, and my son, Matthew, for their constant support and encouragement, without which I could not have written this second edition. John R. O'Malley, undated, presumably around about 2011. Here we go. Contents, Chapter 1, Basic Concepts, Digit Grouping, International System of Units, Electric Charge, Electric Current, Voltage, Dependent Sources, Power, Energy. Chapter 2, Resistance, Ohm's Law, Resistivity, Temperature Effects, Resistors, Resistor Power Absorption, Nominal Values and Tolerances, Color Code, Open and Short Circuits, Internal Resistance. Chapter 3, Series and Parallel DC Circuits, Branches, Nodes, Loops, Meshes, Series, Parallel Connected Components, Kirchhoff's Voltage Law and Series DC Circuits, Voltage Division, Kirchhoff's Current Law and Parallel DC Circuits, Current Division, Kilo Ohm Milliampere Method. Chapter 4, DC Circuit Analysis, Kramer's Rule, Calculator Solutions, Source Transformations, Mesh Analysis, Loop Analysis, Nodal Analysis, Dependent Sources and Circuit Analysis. Chapter 5, DC Equivalent Circuits, Network Theorems and Bridge Circuits. Introduction, Thevenin's and Norton's Theorems, Maximum Power Transfer Theorem, Superposition Theorem, Millman's Theorem, Y delta and delta Y transformations, Bridge Circuits. Operational Amplifier Circuits, Introduction, Op-amp Operation, Popular Op-amp Circuits, Circuits with Multiple Operational Amplifiers. Chapter 7, PSpice DC Circuit Analysis, Introduction, Basic Statements, Dependent Sources, DC and Print Control Statements, Restrictions. Chapter 8, Capacitors and Capacitance, Introduction, Capacitance, Capacitor Construction, Total Capacitance, Energy Storage, Time-Varying Voltages and Currents, Capacitor Current, Single Capacitor DC Excited Circuits, RC Timers and Oscillators. Chapter 9, Inductors, Inductance, and PSpice Transient Analysis, Introduction, Magnetic Flux, Inductance and Inductor Construction, Inductor Voltage and Current Relation, Total Inductance, Energy Storage,
single inductor DC excited circuits, spice transient analysis. Chapter 10, sinusoidal alternating voltage and current, introduction, sine and cosine waves, phase relations, average value, resistor sinusoidal response, effective or RMS values, inductor sinusoidal response, capacitor sinusoidal response. Chapter 11, complex algebra and phasors. Introduction, imaginary numbers, complex numbers and the rectangular form, polar form, phasors. Chapter 12, basic AC circuit analysis, impedance and admittance. Introduction, phasor domain circuit elements, AC series circuit analysis, impedance, voltage division, AC parallel circuit analysis, admittance, current division. Chapter 13, mesh, loop, nodal, and P-spice analyses of AC circuits. Introduction, source transformation, mesh and loop analyses, nodal analysis, P-spice AC analysis. Chapter 14, AC equivalent circuits, network theorems, and bridge circuits. Introduction, Thevenin and Norton's theorems, maximum power transfer theorem, superposition theorem, AC Y delta and delta Y transformations, AC bridge circuits. Chapter 15, power in AC circuits, introduction, circuit power absorption, watt meters, reactive power, complex power and apparent power, power factor correction. Chapter 16, transformers, introduction, right-hand rule, dot convention, the ideal transformer, the air core transformer, the auto transformer, P-spice and transformers. Chapter 17, three-phase circuits, introduction, subscript notation, three-phase voltage generation, generator winding connections, phase sequence, balanced Y circuit, balanced delta load, parallel loads, power, three-phase power measurements, unbalanced circuits, P-spice analysis of three-phase circuits. We got the index on page 415. So this is roughly a 400-page book. And here we go. Chapter 1, basic concepts, digit grouping, international system of units, electric charge, electric current, current in amperes equals coulombs per second, voltage, dependent sources, power, energy, joules equals power times seconds, also kilowatt hours, same thing. Solve problems, charge in coulombs, how many protons, find the current flow, electrons pass to the right through a wire cross section of a ray. What is the current in the wire? In a liquid, negative ions, each with a single surplus electron move. Find the current to the right. Will a 10 amp fuse blow for a steady rate of charge through it of 45,000 C per H? Is that coulombs per hour? I'm not sure. Okay, so this is a multi-part question. Total charge, find the number of coulombs corresponding to 1 amp hour. How long can this battery deliver 2 amps? Find the average drift velocity of electrons. Find the work required to lift a 4,500 kilogram elevator, a vertical distance of 50 meters. Find the potential energy in joules gained by a 180-pound man in climbing a 6-foot ladder. How much chemical energy must a 12-volt car battery expend in moving 8.93 times 10 to the 20 electrons from its positive terminal to its negative terminal? If moving 16 coulombs of positive charge from point B to point A requires 0.8 joules, find VAB, the voltage drop from point A to point B. Okay, find the voltage drop from point A to point B again. Find another voltage drop. Find the energy stored in a 12-volt car battery rated at 650 amp hours. Find the voltage drop across a light bulb. Find the average input power to a radio. How many joules does a 60-watt light bulb consume in 1 hour? How long does a 100-watt light bulb take to consume 13 kilojoules? How much power does a stove element absorb? What current does a 1200-watt toaster draw from a 120-volt line? Find the power absorbed by the voltage source for these circuits. So determine the power absorbed by the independent voltage source and the power absorbed by the dependent voltage source for A, B, and C. Calculate the power absorbed by each component in the circuit. How long can a 12-volt car battery supply 250 amps to a starter motor if the battery has 4 times 10 to the 6 joules of chemical energy that can be converted to electric energy? Find the current drawn from a 115-volt line by a DC electric motor. Find the efficiency of operation of an electric motor. What is the operating efficiency of a fully loaded 12 horsepower DC electric motor? Find the input power to a fully loaded 5 horsepower motor that operates at 80% efficiency. Find the current drawn by a DC electric motor that delivers 2 horsepower. Maximum received solar power is about 1 kilowatt per square meter. If solar panels, which convert solar energy to electric energy, are 13% efficient, how many square meters of solar panels are needed to supply the power to a 1600-watt toaster? What horsepower must an electric motor develop to pump water up to 50 feet at a rate of 2,000 gallons per hour if the pumping system operates at 80% efficiency? 2 systems are in cascade. One operates with an efficiency of 75%, the other with an efficiency of 85%. The input power is 5 kilowatts. What is the output power? Find the conversion relation between kilowatt and joules. For an electric rate of 7 cents per kilowatt hour, what does it cost to leave a 60-watt light bulb on for 8 hours? An electric motor delivers 5 horsepower while operating at an efficiency of 85%. Find the cost for operating it continuously for 1 day if the electric rate is 6 cents per kilowatt hour. Supplementary problems. Find the charge in coulombs of these. How many electrons have a total charge of -4 nanocoulombs? Find the current flow through a switch from a steady movement of 90 coulombs in 6 seconds, 900 coulombs in, and blah, blah, blah. A capacitor is an electric circuit component that stores electric charge. If a capacitor charges at a steady rate of 10 millicoulombs in 0.02 milliseconds, and if it discharges at 1 microsecond at a steady rate, what are the magnitudes of the charging and discharging currents? In a gas, if doubly ionized negative ions move to the right at a steady rate, then find the current to the right, okay? Find the shortest time that 120 coulombs can flow through a 20 amp circuit breaker without tripping it. If a steady current flows into a capacitor, find the time required for the capacitor to ABC, okay. How long can a 4.5 amp hour, 1.5 volt flashlight battery deliver 100 milliamps? Find the potential energy in joules lost by a book falling. How much chemical energy must a 1.25 volt flashlight expend in producing a current flow of 130 milliamps for 5 minutes? Find the work done by a 9-volt battery in moving 5 times 10 to the 20 electrons from its positive terminal to its negative terminal. Find the total energy available from a rechargeable 1.25 volt flashlight. If all the energy in a 9-volt transistor radio battery rated at 0.392 amp hours is used to lift a 150-pound man, how high in feet will he be lifted? That's great. If a charge of -4 coulombs in moving from point A to point B gives up 20 joules of energy, what is the voltage? Moving electrons from point B to point A requires 98 joules of work. Find the voltage. How much power does an electric clock require if it draws this current for this voltage. Find the current drawn by a 1000 watt steam iron from a 120 volt line. For the circuit of figure 111, that was on the oh no, it's just here. Find the power absorbed, blah, blah, blah. Okay. For the circuit of figure 12, then calculate the power absorbed by each component in this. Find the average input power to a radio. Find the voltage drop across a toaster. How many joules does a 40 watt light bulb consume in a day? How long can a 12 volt car battery supply 200 amps? How long does it take a 420 watt color TV set to consume A/B? Find the current drawn by a 110 volt DC electric motor. Find the efficiency of operation of an electric motor. What is the operating efficiency of the DC electric motor that delivers 1 horsepower? Find the current drawn by a 100 volt DC electric motor. What is the horsepower produced by an automobile starter motor that draws 250 amps from a 12 volt battery? What horsepower must an electric motor develop to operate a pump? An AC electric motor drives a DC electric voltage generator. If the motor operates at an efficiency of 90% and the generator at an efficiency of 80%, and if the input power to the motor is 5 kilowatts, find the output power from the generator. Find the cost for 1 year to operate a 20 watt transistor AM FM radio 5 hours a day if electrical energy costs 8 cents per kilowatt hour. For a cost of $5, how long can a fully loaded 5 horsepower electric motor be run? If electric energy costs 6 cents per kilowatt hour, calculate the utility bill for 1 month for operating 8 100 watt light bulbs for 50 hours each, 10 60 watt light bulbs for 70 hours each, and 1 2 kilowatt air conditioner for 80 hours. And then there's a couple of others there as well. Now we're up to chapter 2, resistance. I'm going to talk about Ohm's law, resistivity, temperature effects, resistors, resistor power absorption, nominal values and tolerances, color code, open and short circuits, internal resistance, solve problems. If an oven has a 240 volt heating element with a resistance of 24 ohms, what is the maximum rating of a fuse that can be used in the lines to the heating element? What is the resistance of a soldering iron that draws 0.8333 amps at 120 volts? A toaster with 8.27 ohms of resistance draws 13.9 amps. Find the applied voltage. What is the conductance of a 560 kilo ohm resistor? What is the conductance of an ammeter that indicates 20 amps when 0.01 volts is across it? Find the resistance at 20 degrees Celsius of an annealed copper bus bar, 3 meters in length and 0.5 centimeters by 3 centimeters in rectangular cross section. Find the resistance of an aluminium wire that has a length of 1000 meters and a diameter of 1.626 millimeters. The wire is at 20 degrees Celsius. The resistance of a certain wire is 15 ohms. Another wire of the same material and at the same temperature has a diameter 1/3 as great and the length twice as great. Find the resistance of the second wire. What is the resistivity of platinum if a cube of it 1 centimeter long, each edge has a resistance of 10 microohms across opposite faces? A 15-foot length of wire with a cross-sectional area of 120 C-mils has a resistance of 8.74 ohms at 20 degrees Celsius. What material is the wire made from? What is the length of number 28 AWG nichrome wire required for a 24 ohm resistor at 20 degrees Celsius? A certain aluminium wire has a resistance of 5 ohms at 20 degrees Celsius. What is the resistance of an annealed copper wire of the same size and at the same temperature? A wire 50 meters in length and 2 millimeters squared in cross section has a resistance of 0.56 ohms. A 100 meter length of wire of the same material has a resistance of 2 ohms at the same temperature. Find the diameter of the wire. A wire wound resistor is to be made from 0.2 millimeter diameter Constantan wire wound around a cylinder that is 1 centimeter in diameter. How many turns of wire are required? A number 14 gauge standard annealed copper wire is 0.00323 inches squared in cross section and has a resistance of 2.58 milliamps per foot at 25 degrees Celsius. What is the resistance of 500 feet of number 6 gauge wire if the same material at 25 degrees Celsius? And the cross-sectional area of this wire is 0.0206 inches squared. The conductance of a certain wire is 0.5 S, blah, blah, blah. What is the conductance of the second wire? Find the conductance of 100 feet of number 14 gauge iron wire, which has a diameter of 64 mils. The resistance of a certain copper power line is 100 ohms at 20 degrees Celsius. What is its resistance when the sun heats up the line to 38 degrees Celsius? When 120 volt is applied across a certain light bulb, a half amp current flows, causing the temperature of the tungsten filament to increase to 2600 degrees Celsius. What is the resistance of the light bulb at the normal room temperature of 20 degrees? A certain unenergized copper transformer winding has a resistance of 30 ohms at 20 degrees Celsius. Under rated operation, however, the resistance increases to 35 ohms. Find the temperature of the energized winding. The resistance of a certain aluminium power line is 150 ohms at 20 degrees. Find the line resistance when the sun heats up the line to 42 degrees Celsius. Find the resistance at 35 degrees Celsius of aluminium wire that has length 200 meter and diameter of 1 millimeter. Derive a formula for calculating the temperature coefficient of resistance from the temperature T1 of a material and TO, its inferred zero resistance temperature. Calculate the temperature coefficient of resistance of aluminium at 30 degrees Celsius and use it to find the resistance of aluminium wire at 70 degrees if the wire has a resistance of 40 ohms at 30 degrees. Find the resistance of an electric heater that absorbs 2.4 kilowatts when connected to a 120 volt line. Find the internal resistance of a 2 kilowatt water heater that draws 8.33 amps. What is the greatest voltage that can be applied across a 1/8 watt 2.7 mega ohm resistor without causing it to overheat? If a nonlinear resistor has a voltage current relation of this, what current does it draw when energized by 61 volt? Also, what power does it absorb? At 20 degrees Celsius, a PN junction silicon diode has a current voltage relation is given here. What is the diode voltage when the current is 50 milliamps? What is the resistance range for these things? A voltage of 110 volts is across a 5% 20 kilo ohm resistor. What range must the current be in? What are the colors of the bands on a 10% 5.6 ohm resistor? Determine the colors of the bands on a 20% 2.7 mega ohm resistor. What are the nominal resistance and tolerance of a resistor with color bands in the order of green, blue, yellow, silver from an end of the resistor casing toward the middle? Find the resistance corresponding to color bands in the order of red, yellow, black, gold. If a 12 volt car battery has a 0.04 ohm internal resistance, what is the battery terminal voltage when the battery delivers 40 amps? If a 12 volt car battery has a 0.1 ohm internal resistance, what terminal voltage causes a 4 amp current to flow into the positive terminal? If a 10 amp current source has a 100 ohm internal resistance, what is the current flow from the source when the terminal voltage is 200 volts? Supplementary problems. What is the resistance of a 240 volt electric clothes dryer that draws 23.3 amps? If a voltmeter has 500 kilo ohms of internal resistance, find the current flow through it when it indicates 86 volts. If an ammeter has 2 milliohm of internal resistance, find the voltage across it when it indicates 10 amps. What is the conductance of a 39 ohm resistor? What is the conductance of a voltmeter that indicates 150 volts when 0.3 milliamps flows through it? Find the resistance at 20 degrees of an annealed copper bus bar. What is the resistance of an annealed copper wire that has length of 500 meter and diameter of 0.404 millimeters? The resistance of a wire is 25 ohms. Another wire of the same material and at the same temperature has a diameter twice as great and a length 6 times as great. Find the resistance of the second wire. What is the resistivity of tin of a cube of tin if a cube of it 10 centimeters along each edge has a resistance of 1.5 microohms across opposite faces? A 40-meter length of wire with a diameter of 0.574 millimeters has a resistance of 75.7 ohms at 20 degrees. What material is the wire made from? What is the length of 30 gauge Constantan wire at 20 degrees Celsius required for a 200 ohm resistor? If 29 gauge annealed copper wire at 20 degrees Celsius has a resistance of 83.4 ohms per 1000 feet, what is the resistance per 100 feet of nichrome wire of the same size and at the same temperature? A wire with a resistance of 5.16 ohms has a diameter of 45 mils and a length of 1,000 feet. Another wire of the same material has a resistance of 16.5 ohm and a diameter of 17.9 mils. What is the length of the second wire if both wires are at the same temperature? A wire wound resistor to be made from 30 gauge Constantan wire wound around a cylinder that is half a centimeter in diameter. How many turns are required for a resistance of 25 ohms at 20 degrees? The conductance of a wire is 2.5 S, another wire, blah, blah, blah. Find the conductance of the second wire. Find the conductance of 5 meters of nichrome wire that has a diameter of 1 millimeter. If an aluminium power line has a resistance of 80 ohms at 30 degrees, what is its resistance when cold air lowers its temperature to minus 10 degrees? If the resistance of a Constantan wire is 2 mega ohms at negative 150 degrees, what is its resistance at 200 degrees? The resistance of an aluminium wire is 2.4 ohm at negative 5 degrees. What temperature will it be at 2.8 ohms? What is the resistance of 90 degrees of carbon rod that has a resistance of 25 ohms at 20 degrees? Find the temperature coefficient of resistance of iron at 20 degrees Celsius. What is the maximum current that a 1 watt 56 kilo ohm resistor can safely conduct? What is the maximum voltage that can be safely applied across a half watt 91 ohm resistor? What is the resistance of a 240 volt 5600 watt electric heater? A nonlinear resistor has a voltage current relation of this. Find the current drawn by this resistor when 37 volt is applied across it. If a diode has current voltage relation as given, what is the diode voltage when the current is 150 milliamps? What is the resistance range for a 5% 75 kilo ohm resistor? A 12.1 milliamp current flows through a 10% 2.7 kilo ohm resistor. What range must the resistor voltage be in? What are the resistor color codes for tolerances and nominal resistances given? Find the tolerances and nominal resistances corresponding to the following. A battery provides 6 volt on open circuit and it produces 5.5 volts when delivering 6 amps. What is the internal resistance of the battery? A 3 horsepower automobile electric starter motor operates at 85% efficiency from a 12 volt battery. What is the battery internal resistance if the battery terminal voltage drops to 10 volt when energizing the starter motor? A short circuit across a current source draws 20 amps. When the current source has an open circuit across it, the terminal voltage is 600 volts. Find the internal resistance of the source. A short circuit across a current source draws 15 amps. If a 10 ohm resistor across the source draws 13 amps, what is the internal resistance of the source? I'm going to take a quick break. All right. So up to chapter 3, series and parallel DC circuits. Branches, nodes, loops, meshes, series and parallel connected components. Kirchhoff's voltage law and series DC circuits. Voltage division, Kirchhoff's current law and parallel DC circuits. Current division, kilo ohm milliampere method, solve problems. Determine the number of nodes and branches in the circuit shown. Which components in the figure are in series and which are in parallel. Identify all the loops and all the meshes for a circuit shown in figure 3.4. Also specify which components are in series and which are in parallel. Repeat problem 3.3 for the circuit shown in 3.5. What is the voltage across the open circuit in the circuit shown in the figure? Find the unknown voltages in the circuit. What is the total resistance of 2, 5, 8, 10, 17 ohm resistors connected in series? What is the total resistance of 36 ohm resistors connected in series? What is the total conductance of 4, 10, 16, 20, and 24 Siemens resistors connected in series? A string of Christmas tree lights consists of 6 watt 15 volt bulbs connected in series. That's 8 6-watt bulbs, by the way. What current flows when the string is plugged into a 120 volt outlet? And what is the hot resistance of each bulb? A 30 volt 300 milliamp flashlight bulb is to be used as the dial light in a 120 volt radio. What is the resistance of the resistor that should be connected in series with the flashlight bulb to limit the current? A person wants to move a 20 watt FM AM transmitter radio from a junk car with a 6 volt battery to a new car with a 12 volt battery. What is the resistance of the resistor that should be connected in series with the radio to limit the current, and what is its minimum power rating? A series circuit consists of 240 volts at 12, 20, and 16 ohm resistors. Find the current out of the positive terminal. Okay, a resistor in series with an 8 ohm resistor absorbs 100 watts when the two are connected across a 60 volt line. Find the unknown resistance R. Resistors R1, R2, and R3 are in series with a 100 volt source. Find the total voltage drop across R1. Oh, sorry, they give you the voltage and then you have to find 3 resistances if the total resistance is 50 ohms. Okay. What is the maximum voltage that can be applied across the series combination of 150 ohm 2 watt resistor and a 100 ohm 1 watt resistor without exceeding the power rating of either resistor? Okay. In a series circuit, a current flows from the positive terminal of 180 volt source through the 2 resistors, one of which is 30 ohm resistance and the other which is has 45 volts across it. Find the current and the unknown resistance. Find the current and unknown voltages in the circuit. Find the voltage in the circuit. Find the currents and the voltage in the circuit. This is find the voltage across the 6 ohm resistor. Use voltage division to determine the voltage V4 and V5 in the circuit shown. Find the voltage across the open circuit in the circuit shown. For the circuit shown, calculate I, which is current, and the power absorbed by the dependent source. In the circuit of the figure, determine the resistance seen by the independent voltage source. Find the voltage in the circuit. Calculate current and voltage in the circuit. Determine the voltage drop across the open circuit. Find the unknown currents in the circuit shown. Find current for the circuit shown. Find the short circuit current for the circuit shown. Calculate the voltage of the circuit. Find the total conductance and resistance of 4 parallel resistors having resistances as given. Find the total resistance of 200 ohm resistors connected in parallel. A resistor is to be connected in parallel with a 10 kilo ohm resistor and a 20 kilo ohm resistor to produce a total resistance of 12 kilo ohm. What is the resistance of the resistor? Oh, I see. 3 parallel resistors have a total conductance of 1.75 Siemens. If the 2 resistances are 1 and 2 ohms, what is the third resistance? Without using conductances, find the total resistance of 2 parallel resistors having resistance of 5 and 20 ohms. Repeat problem 3.37 for 3 parallel resistors having resistances 12, 24, and 32 ohms. A 60 watt 100 watt and 200 watt light bulb are connected in parallel across a 120 volt line. Obtain the equivalent hot resistance of this combination from the individual hot resistances of the bulb. Determine RT. Okay. In this connection with series and parallel resistances. Find the total resistance of a resistor ladder network shown in 3.9. In the circuit shown in 3.20, find the total resistance with terminals AB. 90 amp current flows into 4 parallel resistors. Find the current in each resistor. Find the voltage and unknown currents in the circuit shown. Use current division to find currents in the circuit shown. Find the current in the 24 ohm resistor. Calculate voltages in the circuit. Calculate current and voltage in the circuit. Use voltage division twice to find voltage in the circuit shown. Use current division twice to find current in the circuit shown. Supplementary problems. Determine the number of nodes, branches, loops, and meshes in the circuit shown. Find voltages for the circuit. 4 resistors in series have a total resistance of 500 ohm. If 3 of the resistors have resistors 100, 150, 200 ohm, what is the resistance of the 4th resistor? Find the total conductance of some resistors. What is the resistance and minimum power rating of the resistor required? Series circuit consists of DC voltage, blah, blah, blah. Find the source voltage. What is the minimum resistance of the series resistor? Find the unknown resistance. And what is the minimum power rating? And find the voltage in the circuit. And use voltage division to find a voltage. Okay, use voltage division to determine voltage across the 6 ohm resistor. Determine current in the circuit. Find voltage across the open circuit. Find the indicated unknown currents in the circuit shown. Find the short circuit current in the circuit shown. Calculate voltage in the circuit. What are the different resistances that can be obtained with 3 4 ohm resistors? Okay, what is the resistance of the other resistor? Okay, find the equivalent resistance of 4 parallel resistors having resistances 2, 4, 6, and 8 ohms. 3 parallel resistors have a total conductance of 2 millisiemens. If 2 of the resistances are 1 and 5 kilo ohms, what is the third resistance? The equivalent resistance of 3 parallel resistors is 10 ohms. If 2 of the resistors have resistances of 40 and 60 ohms, what is the resistance of the third resistor? Determine the resistance in this expression, and then in this expression, and the total resistance of the ladder network shown. Repeat the problem with resistances doubled. In the circuit shown, find the resistance with terminals A and B. 50 milliamp current flows into 4 parallel resistors. Find each resistor current. Repeat the problem with all resistances doubled. Find the unknown currents in the circuit shown. Find resistances for the circuit shown. In the circuit shown, blah, blah, blah. Use current divisions to find the new current. Find the current in the resistor. What is the resistance in this situation? Find the current in the circuit. What must be the supply voltage for a light bulb to operate under rated conditions? In the circuit, evaluate current and also the power absorbed by the dependent source. Use voltage division twice to find the voltage in the circuit shown. In the circuit shown, use current division twice to calculate the current I in the load resistor. Use repeated current division in finding I in the circuit of figure 342. Chapter 4, DC analysis, Kramer's rule, calculator solutions, source transformations, mesh analysis, loop analysis, nodal analysis, dependent sources and circuit analysis, solve problems, evaluate the following determinants, evaluate the following determinant, Use Cramer's rule to solve for the unknown in these equations. Use Cramer's rule to solve for the unknown in these equations. Transform the voltage sources as shown in the figure to current sources. Transform the current sources shown in the figure to voltage sources. What am I doing? Find the currents down through the resistors in the circuit shown. Then transform the current sources and 2 ohm resistor to an equivalent voltage source, and again find the resistor currents and compare the results. For the circuit in the figure, use repeated source transformations to obtain a single mesh circuit, and then find the current. Find the mesh currents in the circuit shown. Determine the mesh currents in the circuit shown. Obtain the mesh currents in the circuit of figure 414. Find the mesh currents in the circuit shown. Find the mesh currents in the circuit shown. Find the mesh currents in the circuit shown. Use mesh analysis in determining the power absorbed by the dependent voltage in the circuit. Use mesh analysis in finding the voltage V0 in the circuit. Use loop analysis to find the current flowing to the right through the 5 kilo ohm resistor in the circuit shown. Use loop analysis to find the current down through the 8 ohm resistor in the circuit shown. Use two 12 volt batteries are being charged from a 16 volt generator. The internal resistances are 0.5 and 0.8 ohms for the batteries and 2 ohms for the generator. Find the currents flowing into the positive battery terminals. Determine the node voltages in the circuit shown. Find the node voltages in the circuit shown. Use nodal analysis in finding the current in the circuit. Find the node voltages in the circuit. Use nodal analysis to obtain the node voltages V1, V2 in the circuit. Obtain nodal equations for the circuit shown. Obtain the nodal equations for the circuit. We've got to find some voltages. Supplementary problems. Evaluate the following determinants. Use Cramer's rule to solve for the unknowns. Without using Cramer's rule or the matrix calculator approach, solve for the unknowns in these equations. Use Cramer's rule to solve for an unknown in these equations. What is the current source equivalent of a 12 volt battery with a 0.5 ohm internal resistance? What is the voltage source equivalent of a 3 amp current source in parallel with a 2 kilo ohm resistor? Use repeated source transformations in obtaining current in the circuit. Find the mesh currents in the circuit. Solve for the mesh currents in the circuit. Repeat problems with a different voltage. 2 12 volt batteries in parallel provide current to a light bulb that has a hot resistance of 0.5 ohm. If the battery internal resistances are 0.1 and 0.2 ohms, find the power consumed by the light bulb. Determine the current in the circuit. Calculate the mesh currents in the circuit. Find the mesh current in the circuit. Double the voltages of the voltage sources as shown in the earlier figure and redetermine the mesh currents. Compare them with the original mesh currents. Double the resistances of the resistors in the circuit shown in 437 and redetermine the mesh currents. Compare them with the original mesh currents. Repeat the problem with the 3 voltage source changes. For a certain 3 mesh circuit, the self resistances are 20, 25, and 32 ohms for meshes 1, 2, and 3 respectively. The mutual resistances are 10 ohm for meshes 1 and 2, and 12 ohms for meshes 2 and 3, and 6 ohms for meshes 1 and 3. The aiding voltages from the voltages are given. Find the mesh currents. Repeat the problem for the same self resistances and mutual resistances, but for aiding source voltages as given. Obtain the mesh currents in the circuit. Determine the mesh currents in the circuit. Use loop analysis to find current flowing down through the 6 ohm resistor in the circuit. Use loop analysis to find the current flowing to the right through the 8 kilo ohm resistor in the circuit shown. Use loop analysis to find the current in the circuit. Obtain the node voltages in the circuit. Find node voltages in the circuit. Double the currents from the current sources in the circuit shown. Double the conductances of the resistors in the circuit shown and redetermine the node voltages. Compare them with the original. Repeat problems with the amp source changed to -1 amp. Find V0 for the circuit shown in figure 443. Find V in the circuit shown. Calculate the node voltage in the circuit. Find the voltages in the circuit. Find the node voltages in the circuit. Repeat the problem with some changes. For a certain 4-node circuit, including a ground node, the self-conductances are as given. The mutual conductances are as given. Currents flowing are as given. Find the node voltages. Repeat the problem with some changes in the circuit shown. Blah, blah, blah. Okay. So they want you to find VCE. Repeat the problem with the DC voltage source changed. Chapter 5, DC equivalent circuits, network theorems, and bridge circuits. Introduction, Thevenin and Norton's theorems. Maximum power transfer theorem, superposition theorem, Millman's theorem, Y delta and delta Y transformations. That's interesting. Well, that's obviously why they're called that. Now we know. Bridge circuits, solve problems. Okay, so what is the Thevenin equivalent circuit for the battery? Find the Thevenin equivalent circuit. Find the equivalent of Thevenin circuit, find the Norton equivalent. What resistor draws a current of 5 amps when connected across terminals of the circuit as shown. In the circuit, find the base current. Okay. Find the Thevenin equivalent. What is the Norton equivalent? Directly find the output resistance of the circuit shown. Find the Thevenin equivalent of this guy. Obtain the Thevenin equivalent of this. For the circuit, obtain the Thevenin equivalent. Okay, we're going to find the output resistance. We're going to find the input resistance. Find the input resistance of the circuit shown. Find the input resistance Rin. What is the maximum power that can be drawn from a 12-volt battery that has an internal resistance of 0.25 ohms? What is the maximum power that can be drawn by a resistor connected to terminals A, B of the circuit shown? In the circuit, what resistor RL will absorb maximum power, and what is this power? In the circuit of 528, what resistor RL will absorb maximum power, and what is this power? Use superposition to find the power absorbed by the 12 ohm resistor in the circuit shown in figure 529. In the circuit shown, change the 100 volt source to a 360 volt source and the 6 amp current source to an 18 amp source, and use superposition to find the current I. For the circuit shown, use superposition to find the voltage, Thevenin voltage, reference positive on terminal A. The superposition to find Thevenin voltage for the circuit shown. Use Millman's theorem to find the current flowing to a 0.2 ohm resistor from 4 batteries operating in parallel. Use Millman's theorem to find the current drawn by a 5 ohm resistor from the 4 batteries operating in parallel. Use Millman's theorem to find I for the circuit shown. Transform the delta shown in the figure to the Y shown in the other figure. Transform the Y shown in the figure to the delta shown in the figure. Use the delta to Y transformation in finding currents for the circuit shown. Using Y to delta transformation, find the total resistance RT of the circuit shown in figure 536, which has a bridge T attenuator. Find I for the circuit shown. In the circuit shown, what resistor R, replacing the 20 ohm resistor, causes the bridge to be balanced. The slide wire bridge shown in the figure has a uniform resistance wire and is 1 meter long. If balance occurs with the slider at 24 centimeters from the top, what is the resistance of Rx? Supplementary problems. Car battery has 12.1 volt terminal voltage when supplying 10 amps to the car lights. What is this when the starter motor is turned over? The extra 250 amps drawn drops the battery terminal voltages to 10.6 volts. What is the Thevenin equivalent circuit of this battery? In full sunlight, a 2 by 2 centimeter solar cell has a short circuit current of 80 milliamps and the current is 75 milliamps for a terminal voltage of 0.6 volts. What is the Norton equivalent circuit? Find the Thevenin equivalent of the circuit shown in figure 541. In the circuit shown, change the 5 amp current source to a 7 amp current source, the 12 resistor to a 18 ohm resistor, and the 48 volt source to a 96 volt source. Then find the Norton equivalent circuit with the current arrow directed towards terminal A. For the circuit shown in figure 542, find the Norton equivalent with the current IN reference positive towards terminal A. Find the Norton equivalent of the circuit as given. Determine the Norton equivalent. Find the Thevenin equivalent. Okay. In the transistor circuit shown in figure 546, find the base current IB if IC equals 40 IB. Okay. Find the Thevenin equivalent of a transistor circuit as given. Find the current in the circuit shown. Find the Thevenin equivalent of the circuit. Obtain the Thevenin equivalent of the circuit. Find the input resistance at the terminals. Find the output resistance at terminals. Find the input resistance at terminals. Find the output resistance at terminals. What resistor connected between the terminals in the bridge circuit absorbs maximum power, and what is this power? What will be the reading of a zero resistance ammeter connected across terminals of the bridge circuit shown? What will be the reading of a 1 kilo ohm resistor in series with the ammeter? Some solar cells are interconnected for increased power output. Each has the specification given in problem 536. What area of solar cells is required for a power output of 1 watt? Assume a matching load. In the circuit of figure 554, what resistor RL will absorb maximum power, and what is this power? In the circuit of the figure, what resistor connected across the terminals will absorb maximum power, and what is this power? For the circuit shown, use superposition to find the contribution of each source V to VTH, the Thevenin voltage, if it is reference positive towards terminal A. For the circuit shown, use superposition to find the contribution of each source to the current in a short circuit connected between the terminals. In the circuit shown, replace the nonlinear resistor with an open circuit and use superposition to find the contribution of each source to the open circuit voltage reference positive at the top. Okay, blah, blah, blah. Use Millman's theorem to find a load current. Okay. For the automobile circuit, use superposition to find the load current contribution from each source. Transform the delta shown to the Y shown. Repeat the problem for different values. Transformation of the Y shown in the figure to the delta in the figure. Repeat the problem with different values. For the lattice circuits shown, use delta Y transformation to find voltage that makes the current 3 amps. Use delta Y transformation to find the currents in the circuit shown. Use delta to Y transformation in finding the voltage that causes 2 amps to flow through the 3 ohm resistor in the circuit. In the lattice circuit shown, what resistor substituted for the top 40 ohm resistor causes 0 current flow in the 50 ohm resistor? If in the slide wire bridge shown in the figure, balance occurs with the slider at 67 centimeters from the top, what is the resistance Rx? Use a delta Y transformation to find the current in the circuit shown. Remember that for a delta Y transformation, only the voltages and currents external to the delta and Y do not change. In the circuit of the figure, what resistance RL will absorb maximum power, and what is this power? In the circuit of figure, what resistor RL will absorb maximum power, and what is this power? Chapter 6, Operational Amplifier Circuits. Introduction, op-amp operation. Giving you a little bit of a squiz inside there. It's interesting. The paper in this book is really quite thick. Popular op-amp circuits. circuits with multiple op amps, solve problems, perform the following for the circuit, blah, blah, blah. Assume for the sum, okay, blah, blah, blah. So determine the values of resistors that provide the output voltage as given. In the circuits, find the voltage and the current. Then assume op-amp voltage saturation levels and determine the range for linear operation. Calculate voltage and current in the circuit. Determine VL and then repeat. Obtain the input resistance Rn of the circuit. Find for the circuit given, determine the power that will be supplied. Obtain an expression for the voltage. Obtain an expression for the voltage again. For the difference amplifier, okay, find voltage in the circuit. For the op-amp circuit, okay, for the circuit, calculate the voltage VO and the current IO. Determine VO and IO in the circuit. Find VO in the circuit. Determine VO in the circuit. Assume for the op-amp in the circuit that the saturation voltages are VO equals plus or minus 14 volts and that RF equals 6 kiloohms. Then determine the maximum resistance of RA that results in the saturation of the op-amp. In the circuit of the figure, assume that RA equals 2 kiloohms, then find what the resistance of RF must be for the op-amp to operate in the linear mode. Obtain the Thevenin equivalent of the circuit of figure 624 with the Thevenin voltage reference positive at terminal A. Calculate calculate VO in the circuit of the figure. Find VO in the circuit. Determine VO in the circuit. Find V10 and V20 in the circuit. For the circuit given, calculate the voltages. Assume the op-amp saturation voltages are plus or minus 14 volts. Supplementary problems. Obtain an expression for the load. Find VO in the circuit. Assume blah, blah, blah. Okay. So you're going to calculate some resistances. In the circuit of the figure, determine VO and IO. Repeat the problem with different values. For the circuit, for the circuit of the figure, assume that the op-amp saturation voltage is plus or minus 14 volts and that VB equals 0 volts. Determine the range of VA for linear operation. Okay, so determine values for the resistances. Calculate voltage and current. For the op-amp, find the range of VS. For the circuit, calculate voltage and current. Repeat the problem, different values. Determine voltage and current in the circuit. Repeat with different values. Obtain voltage and current in the circuit. Repeat with different values. In the circuit, calculate VO if VS is 4 volts. Assume that the circuit and voltage are as given. Determine the minimum positive value of VS that will produce saturation. Assume for the op-amp circuit that the saturation voltages are VO equals plus or minus 14 volts and that RF equals 12 kiloohms. Calculate the range of values RA that will result in saturation of the op-amp. Assume for the op-amp circuit given in the figure that the op-amp saturation voltages are as given. Determine the range of resistances RF that will result in linear operation. Obtain the Thevenin equivalent of the circuit given. Repeat the problem with different values. Calculate the voltage in the circuit when RF is replaced by an open circuit. Repeat the problem with different values. Calculate voltage in the circuit. Repeat the problem with different values. Determine voltage, 2 voltages in the circuit. And then we're up to Chapter 7, PSpice, DC Circuit Analysis. Introduction. PSpice from Microsim Corporation is a computer program that can be used on many personal computers for the analyses of electric circuits. PSpice is a derivative of SPICE, which is a circuit simulation program that was developed in the 1970s at the University of California at Berkeley. SPICE is an acronym for Simulation Program with Integrated Circuit Emphasis. PSpice was the first derivative of SPICE that was suitable for use on PCs. PSpice and SPICE, which are similar in use, are both used extensively in industry. There are various versions of each. Principally, only the creation of a PSpice circuit file, also called a source file, is presented in this chapter, but much of this material applies as well to the creation of SPICE circuit file. The creation requires the use of a text editor. Typically, there are two text editors that can be used, one of which is in what is called the PSpice control shell. Okay, we got basic statements. Learning SPICE here, very good. Dependent sources. Okay, look at this. DC and print control statements. Restrictions. PSpice requires a DC path to ground from each node. This is seldom a problem for DC circuits, but must be considered for some other circuits, as will be seen. Resistors and voltage sources, and also inductors, provide DC paths, but current sources and capacitors do not. A resistor of huge resistance can always be inserted between a node and ground to provide a DC path. The resistance should be large enough that the presence of the resistor does not significantly affect the circuit operation. Each node must have at least two circuit components connected to it. So that's each node. Each node must have at least two circuit components connected to it. This restriction poses a slight problem at an open circuit. One simple solution is to insert a resistor of huge resistance across the open circuit. Finally, PSpice will not allow a loop of voltage sources or of inductors. The insertion of a resistor in series with one of the voltage sources will eliminate this problem. The resistance should be small enough that the presence of the resistor does not significantly affect the circuit operation. Okay, now we get some solved problems. So repeat the problem of 411 using PSpice. Okay, repeat the problem using PSpice. Repeat another problem using SPICE. Repeat a problem using SPICE. Again, repeating problem with PSpice. Repeating problem with SPICE. Repeat problem with SPICE. Repeat problem with SPICE. Repeat problem with SPICE. Supplementary problems. Use PSpice to compute the current in this circuit. Use PSpice to determine the current in this circuit. Use PSpice to find the Thevenin voltage. Cool. Use PSpice to obtain VO in the circuit. And again, and using PSpice to determine the output corresponding to the following circuit file. Without using PSpice, determine the output corresponding to the following circuit file. Again, learning how to read PSpice. Very cool. Okay, Chapter 8, Capacitors and Capacitance. Introduction. Capacitance, capacitor construction, total capacitance, energy storage, time-varying voltages and currents, single capacitor DC excited circuits, this capacitor currents, RC timers and oscillators, solve problems. Find the capacitor of an initially uncharged capacitor, find the capacitance of an initially uncharged capacitor for which the movement of 3 times 10 to the 15 electrons from one capacitor plate to another produces 200 volt capacitor voltage. What is the charge stored on a 2 microfarad capacitor with 10 volts across it? What is the change of voltage produced by 8 times 10 to the 9 electrons moving from one plate to the other in an initially charged 10 picofarad capacitor? Find the capacitance of a parallel plate capacitor if the dimensions of each rectangular plate is 1 by 0.5 centimeters and the distance between the plates is 0.1 millimeter. The dielectric is air. Also, find the capacitance if the dielectric is mica instead of air. Find the distance between the plates of a 0.01 microfarad parallel plate capacitor if the area of each plate is 0.07 meters squared and the dielectric is glass. Capacitor has a disc-shaped dielectric of ceramic that has a 0.5 centimeter diameter and is 0.521 millimeter thick. The disc is coated on both sides with silver, this coating being the plates. Find the capacitance. A 1 farad parallel plate capacitor has a ceramic dielectric 1 millimeter thick. If the plates are square, find the length of a side plate. What are the different capacitances that can be obtained with a 1 and 3 microfarad capacitor? Find the total capacitance, CT, of the circuit shown. A 4 microfarad capacitor, a 6 microfarad capacitor, and an 8 microfarad capacitor are in parallel across a 300 volt source. Find some of the parameters. Repeat the problem for capacitors in series instead of parallel, but find each capacitor voltage instead of each charge stored. 25 volt source and 2 capacitors are connected in series. If one capacitor has 20 microfarads of capacitance and has 16 volt across it, what is the capacitance of the other capacitor? Find each capacitor voltage in the circuit shown. Find each capacitor voltage in the circuit shown. Okay, we're going to find the voltage and also the initial and final stored energies. Repeat the problem, different values. Find the voltage and the initial and final stored energies. What is the current flowing through a 2 microfarad capacitor when the capacitor voltage is 10 volts? If the voltage across a 0.1 microfarad capacitor is 3000 TV, find the capacitor current. I don't know what that T means. Maybe that's a typo. I don't know. Sketch the waveform of the current that flows through a 2 microfarad capacitor when the capacitor voltage is as shown. As always, assume associated references because there is no statement to the contrary. Find the time constant of the circuit shown. How long does a 20 microfarad capacitor charged to 150 volts take to discharge through a 3 mega ohm resistor? Also, at what time does the maximum discharge current occur and what is its value? At t equals 0 seconds, a 100 volt source is switched in series with a 1 kilo ohm resistor and an uncharged 2 microfarad capacitor. And then there's a bunch of questions. What are the initial capacitor voltage, the initial current, the initial rate of capacitor voltage increase, the time required for the capacitor voltage to reach maximum value? Repeat the problem with different values in the circuit shown. Blah, blah, blah. Find these voltages and currents a long time after the switch closes. A 2 microfarad capacitor initially charged to 300 volts is discharged through a 270 kilo ohm resistor. What is the capacitor voltage at 20.25 seconds after the capacitor starts to discharge? Closing a switch connects a series. Closing a switch connects in series a 200 volt source, a 2 mega ohm resistor, and an uncharged 0.1 microfarad capacitor. Find the capacitor voltage and current at 0.1 second after the switch closes. For the circuit used in the problem 827, find the time required for the capacitor voltage to reach 50 volts. Then find the time required for the capacitor voltage to increase another 50 volts from 50 to 100 volts. Compare the times. In the circuit shown, the switch closes at t equals 0 seconds. Find VC and I for t greater than 0 seconds. If VC is 0, is 100 volts. The switch is closed at t equals 0 in the circuit. Find I for t greater than 0. the capacitor is initially uncharged. After a long time in position 1, the switch in the circuit shown is thrown to position 2 at t equals 0 for a duration of 30 seconds and then return to position 1. Find the equations for V for time greater than or equal to 0 seconds. Find V at t equals 5 seconds, at t equals 40 seconds, and then make a sketch for V in the period 0 seconds to 80 seconds. A simple RC timer has a switch that, when closed, connects in series a 300 volt source, a 16 mega ohm resistor, and an uncharged 10 microfarad capacitor. Find the time between the closing and opening of the switch if the capacitor charges 10 volts during this time. Repeat the problem with different voltages. For the oscillators shown, find the period of oscillation. Repeat the problem with different voltage source. Supplementary problems. What electron movement between the plates for 0.1 microfarad capacitor produces a 110 volt change of voltage? If the movement of 4.68 times 10 to the 14 electrons between the plates of a capacitor produces a 150 volt change in capacitor voltage, find the capacitance. What change in voltage of a 20 microfarad capacitor is produced by a movement of 9 times 10 to the 14 electrons between the plates? A tubular capacitor consists of 2 sheets of aluminium foil, 3 centimeters wide and 1 meter long, rolled into a tube with separating sheets of waxed paper of the same size. What is the capacitance of if the paper is 0.1 millimeters thick and has a dielectric constant of 3.5? Find the area for each plate of a 10 microfarad parallel plate capacitor that has a ceramic dielectric of 0.5 millimeters thick. Find the thickness of the mica dielectric of a 10 picofarad parallel plate capacitor if the area of each plate is 10 to the minus 4 meters squared. Find the diameter of a disc shaped 0.001 microfarad that has a ceramic dielectric 1 millimeter thick. What are the different capacitances that can be obtained with a 1 microfarad capacitor, a 2 microfarad capacitor, and a 3 microfarad capacitor? Find the total capacitance CT of the circuit shown. A 5, 7, and 9 microfarad capacitor are in parallel across a 200 volt source. Find the magnitude of charge stored by each capacitor and the total energy stored. A 6, 16, and 48 microfarad capacitor are in series with a 180 volt source. Find the voltage across each capacitor and the total energy stored. 2 capacitors are in series across a 50 volt source. If one is 1 microfarad capacitor with 16 volt across it, what is the capacitance of the other? Find each capacitor voltage in the circuit shown. A 0.1 microfarad capacitor charged to 100 volts and a 0.2 microfarad capacitor charged to 60 volts are connected together with plates of the same polarity joined. Find the voltage and the initial and final stored energy. Repeat the problem with different polarity. Find the voltage across a capacitor when the capacitor current is 0.5 milliamp. Repeat the problem with different specs. If the voltage across a 2 microfarad capacitor is given, blah, 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 find the capacitor current. Find the time constant of the circuit shown. Find the time constant of the circuit shown. How long does it take a 10 microfarad capacitor charged to 200 volts to discharge through a 160 kilo ohm resistor? And what is the total energy dissipated in the resistor? Okay. At t equals 0, the closing of a switch connects a series of 150 volts in series, a 150 volt source, a 1.6 kilo ohm resistor, and the parallel combination of a 1 kilo ohm resistor and an uncharged 0.2 microfarad capacitor, and find these various things. Repeat the problem with different specs. In the circuit shown, find the indicated voltages and currents. Immediately after the switch closes, notice that the current source is active in the circuit before the switch closes. In the circuit shown, find the indicated voltages and currents. A 0.1 microfarad capacitor initially charged at 230 volts is discharged through a 3 mega ohm resistor. Find the capacitor voltage at 0.2 seconds after the capacitor starts to discharge. for the circuit described in the problem 861. How long does it take the capacitor to discharge to 40 volts? Closing a switch connects in series a 300 volt source, a 2.7 mega ohm resistor, and a 2 microfarad capacitor charged to 50 volts with its positive plate towards the positive terminal of the source. Find the capacitor current 3 seconds after the switch closes. Also find the time required for the capacitor voltage to reach 250 volts. The switch is closed at t equals 0. In the circuit shown, find voltage and current for t greater than 0. The capacitor is initially uncharged. Repeat the problem with different values. After a long time in position 1, the switch in the circuit is thrown. Find the voltage. Okay. After a long time in position 2, the switch is thrown. Find the voltage. A simple RC timer has a 50 volt source, a switch, and an uncharged 1 microfarad capacitor and a resistor all in series. Closing the switch and then opening it 5 seconds later produces a capacitor voltage of 3 volts. Find the resistance of the resistor. Repeat problem 8.68 for a capacitor voltage of 40 volts. In the oscillator circuit shown, replace the 1 mega ohm resistor with a 4.3 mega ohm resistor and the 1000 volt source with a 150 volt source, and find the period of oscillation. All right. It's going to take a bit of a break before we continue with chapter 9. All right, on we go. Chapter 9, inductors, inductance, and P-spice transient analysis. Introduction, magnetic flux, inductance and inductor construction, inductor voltage and current relation, total inductance, energy storage, single inductor DC excited circuits, P-spice transient analysis, solve problems. Find the voltage induced in a 50-turn coil from a constant flux of 10 to the 4 Webers and also from a changing flux of 3 Webers per second. What is the rate of change of flux linking a 200-turn coil when 50 volts is across the coil? Find the number of turns of a coil for which a change of 0.4 Webers per second of flux linking the coil induces a coil voltage of 20 volts. Find the inductance of a 100-turn coil that is linked by 3 times 10 to the minus 4 Webers when a 20 milliamp current flows through it. Find the approximate inductance of a single layer coil that has 300 turns wound in a plastic cylinder 12 centimeters long and 0.5 centimeters in diameter. Find the approximate inductance of a single layer 50-turn coil that is wound on ferromagnetic cylinder 1.5 centimeters long and 1.5 millimeters in diameter. The ferromagnetic material has a relative permeability of 7,000. A 3 Henry inductor has 2,000 turns. How many turns must be added to increase the inductance to 5 Henry? Find the voltage induced in a 150 millihenry coil when the current is constant at 4 amp. Also, find the voltage when the current is changing at a rate of 4 amps per second. Find the voltage induced in a 200 millihenry coil at t equals 3 milliseconds if the current increases uniformly from 30 milliamps at t equals 2 milliseconds to 90 milliamps at t equals 5 milliseconds. What is the inductance of a coil for which a changing current increasing uniformly from 30 milliamps to 80 milliamps in 100 microseconds induces a 50 millivolts in the coil? Find the voltage induced in a 400 millihenry coil from 8 seconds to 0 seconds to 8 milliseconds when the current shown in the figure flows through the coil. Find the total inductance of 3 parallel inductors having inductances of 45, 60, and 75 millihenries. Find the inductance of the inductor that, when connected in parallel with a 40 millihenry inductor, produces a total inductance of 10 millihenries. Find the total inductance LT of the circuit shown. Find the energy stored in a 200 millihenry inductor that has 10 volts across it. A current of I equals 0.32 TA flows through a 150 millihenry inductor. Find the energy stored at T equals 4 seconds. Okay, find the time constant of the circuit shown. What is the energy stored in the inductor for the circuit shown? Closing the switch connects a series 20 volt source, a 2 ohm resistor, and a 3.6 Henry inductor. How long does it take the current to get to its maximum value, and what is this value? Closing the switch connects a series 21 volt source, a 3 ohm resistor, and a 2.4 Henry inductor. Find the initial and final currents, the initial and final inductor voltages, and the initial rate of current increase. A closed switch connects a 120 volt source to the field coils for DC motor. These coils have 6 Henry of inductance and 30 ohms of resistance. A discharge resistor in parallel with the coil limits the maximum coil and switch voltages at the instance at which the switch is open. Find the maximum value of the discharge resistor that will prevent coil voltage from exceeding 300 volts. In the circuit shown in the figure, find the indicated currents a long time after the switch has been in position 1. For the circuit shown, find the indicated voltage and currents immediately after the switch is thrown to position 2 from position 1, where it has been a long time. A short is placed across a coil that at the time is carrying half an amp. If the coil has an inductance of 0.5 Henrys and a resistance of 2 ohms, what is the coil current 0.1 seconds after the short is applied? A coil for a relay has a resistance of 30 ohms and an inductance of 2 Henry. If the relay requires 250 milliamps to operate, how soon will it operate after 12 volts is applied to the coil? For the circuit shown, find V and I for t greater than 0 seconds. If at t equals 0 seconds, the switch is thrown to position 2 after having been in position 1 for a long time. For the circuit shown, find I for t greater than or equal to 0, if the switch is closed at t equals 0 after being open for a long time. In the circuit shown, switch S1 is closed at t equals 0, and then switch 2 is open at t equals 3 seconds. Find the current at 2 and the current at 4. That's seconds, I guess, and make a sketch for t greater than 0 seconds. Use P-Spice to find the current in the circuit. Okay. In the circuit, the switch is moved at t equals 0 and then back at t equals 2. The initial capacitor voltage is given. Find voltage by hand and also using P-Spice. Okay. Supplementary problems. Find the voltage induced in a 500 turn coil when the flux changes uniformly by 16 times 10 to the minus 5 Webers in 2 milliseconds. And find the change in flux linking an 800 turn coil when 3.2 volts is induced for 6 milliseconds. What is the number of turns of a coil for which a flux change of 40 times 10 to the minus 6 Webers in 0.4 milliseconds induces a 70 volt in the coil? Find the flux linking a 500 turn 0.1 Henry coil carrying a 2 milliamp current. Find the approximate inductance of a single layer 300 turn air core coil that is 3 inches long and 0.25 inches in diameter. Find the approximate inductance of a single layer 500 turn coil that is wound on a ferromagnetic cylinder that is 1 inch long and 0.1 inch in diameter. The ferromagnetic material has a relative permeability of 8,000. A 250 millihenry inductor has 500 turns. How many turns must be added to increase the inductance to 400 millihenries? The current in a 300 millihenry inductor increases uniformly from 0.2 to 1 amp in 0.5 seconds. What is the inductor voltage for this time? If a change in current in a 0.2 Henry inductor produces a constant 5 volt inductor voltage, how long does the current take to increase from 30 to 200 milliamps? What is the inductance of a coil for which a change in current increasing uniformly from 150 to 275 milliamps in 300 microseconds uses 750 millivolts in the coil? Find the voltage induced in a 200 millihenry coil from 0 to 5 milliseconds when a current I, described as follows, flows through the coil. Find the total inductance of 4 parallel inductors having inductances of 80, 125, 200, and 350 millihenries. Find the total inductance of a 40 millihenry inductor in series with the parallel combination of a 60 millihenry inductor, an 80 millihenry inductor, and a 100 millihenry inductor. A 2 Henry inductor at 430 ohm resistor and a 50 volt source have been connected in series for a long time. What is the energy stored in the inductor? A current of I equals 0.56 TA flows through a 0.5 Henry inductor. Find the energy stored at T equals 6 seconds. What is the energy stored by the inductor in the circuit shown? Find the time constant of the circuit shown. How long after a short circuit is placed across a coil carrying a current of 2 amp does the current go to 0 if the coil has 1.2 henries of inductance and 40 ohms of resistance? Also, how much energy is dissipated? A switch closing connects in series a 10 volt source, an 8.2 ohm resistor, and a 1.2 Henry inductor. How long does the current take to reach its maximum value, and what is this value? In closing, a switch connects a 100 volt source with a 5 ohm of internal resistance across the parallel combination of a 20 ohm resistor and a 0.4 Henry inductor. What are the initial and final source currents, and what is the initial rate of inductor current increase? In the circuit shown, the switch is thrown at T equals 0 from an open position to position 1. Find the indicated currents and also at a long time later. Okay, in the circuit shown, the switch is thrown at T equals 0 to position 2 from position 1 where it has been a long time. Find the indicated currents at T equals 0 plus S and also at a long time after. Okay. Switch closing at T equals 0 connects a 20 millihenry conductor to a 40 volt source that has 10 ohms of internal resistance. Find the inductor voltage and current for T greater than 0. A switch closing at T equals 0 connects a 100 volt source with a 15 ohm internal resistance to a coil that has 200 millihenry of inductance and 5 ohms of resistance. Find the coil voltage for T greater than 0. A coil for a relay has a resistance of 20 ohm and an inductance of 1.2 Henry. The relay requires 300 milliamps to operate. How soon will the relay operate after a 20 volt source with a 5 ohm of internal resistance is applied to the coil? Assume that the switch in the circuit shown has been closed a long time. Find I as a function of time after the switch opens at T equals 0. In the circuit shown, the switch is thrown to position 1 at T equals 0 after being open a long time. Then it is thrown to position 2 at T equals 2.5 seconds. Find I for T greater than 0, T greater than or equal to 0. Obtain the expression for the response for T greater than or equal to 0 corresponding to the following circuit file. Also from this expression, determine the 11th value that will be printed. Obtain the expression for the response for T greater than or equal to 0 corresponding to the following circuit file. Also from this expression, determine the 9th value that will be printed. Obtain the expression for the response T greater than or equal to 0 corresponding to the following circuit file. Also from these expressions, determine the 17th value that will be printed. And again, determine the results of a SPICE file. Chapter 10, about halfway through. All right. sinusoidal alternating voltage and current. Introduction, sine and cosine waves, phase relations, average value, resistor sinusoidal response, effective or RMS values, inductor sinusoidal response, capacitor sinusoidal response. So problems. Find the periods of periodic voltages that have frequencies of A, B, or C. Find the frequencies of periodic currents that have periods of A, B, or C. What are the period and frequency of a periodic voltage that has 12 cycles in 46 milliseconds? Find the period, the frequency, and the number of cycles shown for the periodic wave illustrated in the figure. Convert the following angles in degrees to angles in radians. Convert the following angles in radians to angles in degrees. Find the periods and frequencies of sinusoidal currents that have radian frequencies as given. Find the radian frequencies of sinusoidal voltages that have periods as given. Find the amplitudes of frequencies A and B. Okay, find the instantaneous value of V equals 70 sine 400 pi TV at t equals 3 milliseconds. A current sine wave has a peak of 58 milliamps and a radian frequency of 90 radians per second. Find the instantaneous current at t equals 23 milliseconds. Evaluate A, B at t equals 1.1 milliseconds. Find expressions for the sinusoid shown in the figure. Sketch a cycle of V equals 30 sine 754 t plus 60 degrees V for the period beginning at t equals 0. Have all three abscissa units of time, radians, and degrees. What is the shortest time required for a 2.1 kiloradian per second sinusoid to increase from 0 to 4/5 of its peak value? If 50 volts is the peak voltage inducted in the conductor of an alternator shown in figure 10.2, find the voltage induced after the conductor has rotated through an angle of 35 degrees from its vertical position. If the conductor in the alternator shown in figure 10.2 is rotating at 60 Hz, and if the induced voltage has a peak of 20 volts, find the induced voltage 20 milliseconds after the conductor passes through a horizontal position if the voltage is increased then. Find the periods of A, B, and C. Find the phase relations for the following pairs of sinusoids. Find the angle by which this leads to this. Find the average values of the periodic waveforms shown in figure 10.8. What are the average values of the periodic waveforms shown in figure 10.9? What is the average power absorbed by a circuit component that has a voltage V equals blah, 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 across it when the current equals blah, blah, blah? As assume associated references since there is no statement to the contrary. If the voltage across a single circuit component is as given, for a current through it as given, and if the references are associated, it should be assumed, what is the component? The voltage across a 62 ohm resistor is as given. Find the resistor current and plot one cycle of the voltage and current waveforms on the same graph. Okay, a 30 ohm resistor has a voltage as given. What is the average power dissipation of the resistor? Find the average power absorbed by a 2.7 ohm resistor when the current is this. Okay, what is the peak voltage at a 120 volt electric outlet? What is the reading of an AC voltmeter connected across a 680 ohm resistor that has a current of this flowing through it? What is the reading of an AC voltmeter connected across a 10 ohm resistor that has a peak power dissipation of 40 watts? What is the expression for a 240 Hz sine wave of voltage that has an RMS value of 120 volts? Find the effective value of a periodic voltage that has a value of 20 volts for one half period and minus 10 volts for the other half period. Find the effective value of the periodic current shown in figure 1011a. Find the reactances of a 120 millihenry inductor at A, B, C, or D hertz. Find the inductances of the inductors that have reactances of A, B, and C. Find the frequencies at which a 250 millihenry inductor has reactances of 30 ohms and 50 kiloohms. What is the voltage across a 30 millihenry inductor that has 40 milliamps, 60 hertz current flowing through it? The voltage given is across an inductor that has a resistance of 62 ohms. Find the inductor current and plot one cycle of the voltage and current on the same graph. Find the voltages across a 2 Henry inductor for the following currents. Find the reactances of a 0.1 microfarad capacitor at A, B, C, and D. Find the capacitances of capacitors that have a reactance of minus 500 ohms at A, B, and C megahertz. Find the frequencies at which a 2 microfarad capacitor has reactances of minus 0.1 and minus 2,500 ohms. What current flows through a 0.1 microfarad capacitor that has 200 volts at 400 hertz across it? What is the voltage across a capacitor that carries 120 milliamps current if the capacitive reactance is minus 230 ohms? The voltage given is across a capacitor that has a reactance of negative 62 ohms. Find the capacitor current and plot one cycle of the voltage and current on the same graph. What current flows through a 2 microfarad capacitor for voltages of A and B? Supplementary problems. Find the periods of periodic currents that have frequencies of A, B, and C megahertz. What are the frequencies of periodic voltages that have periods of A, B, and C time? What are the period and frequency of a periodic current for which 423 cycles occur in 6.19 milliseconds? Convert the following angles in degrees to angles in radians. Okay, convert the following angles in radians to degrees. Find the period of sinusoidal voltages that have radian frequencies as given. Find the radian frequencies of sinusoidal currents that have periods as given. What are the amplitudes and frequencies of these expressions? Find the instantaneous value of this current at these times. What is the frequency of a sine wave of voltage which has 45 volts peak and which continuously increases from 0 volts at t equals 0 to 24 volts at t equals 46.2 milliseconds? If a voltage cosine wave has a peak value of 20 volts at t equals 0, and if it takes a minimum of 0.123 seconds for this voltage to decrease from 20 volts to 17 volts, find the voltage at t equals 4.12 seconds. What is the instantaneous value of this current at these times? Find an expression for a 400 hertz sinusoidal current that has a 2.3 amp positive peak at t equals minus 0.45 milliseconds. Find an expression for a sinusoidal voltage that is 0 volts at t equals minus 8.13 milliseconds, after which it increases to a peak of 15 volts at t equals 6.78 milliseconds. What is the shortest time required for a 4.3 kiloradians per second sinusoid to increase from 2/5 to 4/5 of its peak value? If 43.7 volts is the peak voltage induced in the conductor of the alternator shown in figure 10.2, find the voltage induced after the conductor has rotated through an angle of 45 degrees from its horizontal position. If the conductor of the alternator of figure 10.2 is rotating at 400 hertz, and if the induced voltage has a 23 volt peak, find the induced voltage 0.23 milliseconds after the conductor passes through its vertical position. Find the periods of A, B, and C. Find the phase relations for the following pair of sinusoid. Find the average value of a half-wave rectified sinusoidal voltage that has a peak of 12 volts. This wave consists only of the positive half cycles of the sinusoidal voltage. It is 0 during the times that the sinusoidal is negative. Find the average values of the periodic waveforms shown in figure 10.14. What is the average power absorbed by a circuit component that has a voltage V equals 10 volts across it when the current is given? Find the average power absorbed by a circuit component that has a voltage as given across it with the current as given flowing through it. What is the conductance of a resistor that has a voltage as given across it when the current as given flows through it? If the voltage as given is across a 33 kilo ohm resistor, what is the resistor current? Find the average power absorbed by an 82 ohm resistor that has a voltage as given across it. What is the average power absorbed by a 910 ohm resistor that has a current as given flowing through it? Find the average power absorbed by a resistor having a voltage as given across it and a current as given flowing through it. What is the reading of an AC ammeter that is in series with a 470 ohm resistor that has a voltage as given across it? What is the reading of an AC ammeter that is in series with a 270 ohm resistor that has a peak power dissipation of 10 watts? What is the expression for a 400 Hertz current cosine wave that has an effective value of 13.2 milliamps? Find the effective value of voltage as given. Use a sinusoidal identity in finding the average value of the squared voltage. Find the effective value of a periodic current that has a value of 40 milliamps for 2/3 of a period and 25 milliamps for the remaining 1/3 of the period. Would the effective value be different if the current were negative 25 milliamps instead of 25 milliamps for the one period? Find the effective value of a periodic current that in a 20 millisecond period has a value of 0.761 amps for 4 milliseconds, 0 amps for 2 milliseconds, minus 9.25 amps for 8 milliseconds, and 1.3 amps for the remaining 6 milliseconds. Would the effective value be different if the time segments were in seconds instead of milliseconds? Find the resistances of a 180 millihenry inductor at A, B, or C kilohertz. Find the inductances of the inductors that have reactances as given. What are the frequencies at which a 120 millihenry inductor has reactances of A or B? What current flows through an 80 millihenry inductor that has 120 volts at 60 hertz across it? What is the inductance of the inductor that will draw a current of 250 milliamps when connected to a 120 volt 60 hertz voltage source? What are the currents that flow in a 500 millihenry inductor for voltages of A and B? Find the reactances of a 0.25 microfarad capacitor at A, B, and C megahertz. Find the capacitances of the capacitors that have reactances of A, B, and C in kilohertz. Find the frequency at which 0.1 microfarad capacitor and a 120 millihenry inductor have the same magnitude of reactance. What is the capacitance of a capacitor that draws 150 milliamps when connected to a 100 volt 400 hertz voltage source? What are the currents that flow in a 0.5 microfarad capacitor for capacitor voltages of A equals V, A for A B, and B, okay. And what are the voltages across a 2 microfarad capacitor for currents of A and B? Chapter 11, Complex Algebra and Phasors. Introduction, Imaginary Numbers, Complex Numbers and the Rectangular Form, Polar Form, Phasors. By definition, a phasor is a complex number associated with a phase-shifted sine wave such that if the phasor is in polar form, its magnitude is the effective RMS value of the voltage or current, and its angle is the phase angle of the phase-shifted sine wave. For example, blah, 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 blah. All right, off we go. Solve problems. Perform the following operations. So you're going to add up some imaginary numbers, complex numbers. Add or subtract as indicated, and express in rectangular form. Find the following products and express in rectangular form. Evaluate, that. Evaluate that. Find the following quotients in rectangular form. Convert the following numbers to polar form. Convert the following numbers to rectangular form. Find the following products in polar form. Find the quotients in polar form. Find the following quotient. Find the corresponding phasor voltages and currents for the following. Find the voltages and currents corresponding to the following phasor voltages and current. Find a single sinusoid that is the equivalent of each of the following. For the circuit shown, find Vs. In the circuit shown, voltmeters VM1 and VM2 have readings of 40 and 30 volts respectively. Find the reading of voltmeter VM3. Find Vs for the circuit shown. Find Is for the circuit shown. If two currents have phases of 10 per 0 degrees and that's I see, yeah, that's the phasor. 10, 0 and 730 milliamps. What is the angle and RMS value of the current that is the sum of these currents? Solve by using a funicular diagram. Check the answer by using complex algebra. A synchronous motor draws a 9 amp current from a 240 volt 60 hertz source. A parallel induction motor draws 8 amps. If the synchronous motor current leads the applied voltage by 20 degrees, and if the induction motor current lags the voltage by 30 degrees, what is the total current drawn from the source? Find this current graphically and algebraically. Supplementary problems. Perform the following operations. Some math. Perform the following operations and express the results in rectangular form. Find the following products and express in rectangular form. Find the following products and express in rectangular form. Evaluate this, this, and this. Find the following quotients. Convert each of the following to polar form. Convert each of the following to rectangular form. Perform the following operations and express the results in polar form. Find the following products in polar form. Find the following quotients in polar form. Find the following quotients in polar form. Find the following quotient in polar form. Find the corresponding phasor voltages and currents of the following in polar form. Find the voltages and currents corresponding to the following phasor voltages and currents. Each sinusoid has a radiant frequency of 750 radians per second. Find the single sinusoid that is the equivalent of each of the following. In figure 11.9, find current 1 and current 2. In the circuit shown in figure 11.10, ammeters A1, A2 have readings of 4 and 3 amps respectively. What is the reading of ammeter 3? A current I as given flows through a 3.3 kilo ohm resistor in series with the 0.5 microfarad capacitor. Find the voltage across the series combination. Of course, as always, assume associated references when, as here, there is no statement to the contrary. A voltage V as given is across a 680 ohm resistor in parallel with a 1 Henry inductor. Find the current flowing into this parallel combination. A current I as given flows through the series combination of a 91 ohm resistor, a 120 millihenry inductor, and a 20 microfarad capacitor. Find the voltage across the series combination. The voltage V as given is across the parallel combination of a 10 kilo ohm resistor, a 100 millihenry inductor, and a 10 microfarad capacitor. Find the total current flowing into the parallel combination. Also find the inductor current IL and compare peak values of IL and IT. Chapter 12, Basic AC Circuit Analysis, Impedance and Admittance. Introduction, Phasor Domain Circuit Elements. AC Series Circuit Analysis. impedance, voltage division, AC parallel circuit analysis, admittance, current division. Solve problems. Find the total impedance in polar form of a 0.5 Henry inductor and a series 20 ohm resistor at A, B, and C hertz. A 200 ohm resistor, a 150 millihenry inductor, and a 2 microfarad capacitor are in series. Find the total impedance in polar form at 400 hertz. Also draw the impedance diagram and the impedance triangle. A 2000 ohm resistor, a 1 Henry inductor, and a 0.01 microfarad capacitor are in series. Find the total impedance in polar form at A, B, and C radians per second. A coil energized by 120 volts at 60 hertz draws 2 amp current that lags the applied voltage by 40 degrees. What are the coil resistance and inductance? A load has a voltage as given and a current as given at a frequency of 400 hertz. Find the two element series circuit that the load could be. Assume associated references, of course. Okay, a 20 ohm resistor is in series with a 0.1 microfarad capacitor. At what radian frequency are the circuit voltage and current out of phase by 40 degrees? A 200 millihenry inductor and a resistor in series draw 0.6 amps when 120 volts at 100 hertz is applied. Find the impedance in polar form. What capacitor in series with a 750 ohm resistor limits the current to 0.2 amps when 240 volts at 400 hertz is applied? A capacitor is in series with a coil that has a 1.5 Henry of inductance and 5 ohms of resistance. Find the capacitance that makes the combination purely resistive at 60 hertz. 3 circuit elements in series draw a current of 10 sine 400t plus 70 degrees amps in response to an applied voltage of this. If one element is a 16 millihenry inductor, what are the two other elements? Find the input impedance at 5 kiloradians per second of the circuit shown. A 240 volt source is connected in series with two components, one of which has an impedance of 60, I don't know how you say polar form, I don't know how you express that, 80 angle 60 degrees ohms. What is the impedance of the other component if the current that flows is 2 amps and if it leads the source by voltage by 40 degrees? Find the total impedance of two parallel components that have impedance as given. Find the total impedance at 1 kiloradians per second of a 1 Henry conductor at 1 microfarad capacitor connected in series and also in parallel. Okay. What capacitor and resistor connected in series have the same total impedance at 400 radians per second as a 10 microfarad capacitor and a 500 ohm resistor connected in parallel? What two circuit elements connected in series have the same total impedance? I'm just going to take a break. I'm back. I lost my place. I'll just continue from here. So a capacitor is in series with a coil that has 1.5 Henry of inductance and 5 ohms of resistance. Find the capacitance that makes the combination purely resistive at 60 hertz. The 3 circuit elements in series draw a current of this in response to an applied voltage of this. If one element has a 60 millihenry inductor, what are the two other elements? Find the input impedance at 5 kiloradians per second of the circuit shown. A 240 volt source is connected in series with two components, one of which has an impedance of 80 angle 60 degrees ohms. What is the impedance of the other component if the current that flows is 2A and if it leads the source voltage by 40 degrees? Find the total impedance of two parallel components that have impedance as given. Find the total impedances at 1 kiloradians per second of 1 Henry inductor and 1 microfarad capacitor connected in series and also in parallel. What capacitor and resistor connected in series have the same total impedance at 400 radians per second as a 10 microfarad capacitor and a 500 ohm resistor connected in parallel? What two circuit elements connected in series have the same total impedance at 4 kiloradians per second as the parallel combination of 50 microfarad capacitor and a 2 millihenry coil with a 10 ohm winding resistance? For the circuit shown, find the indicated unknown phases and the corresponding sinusoids. The frequency is 60 Hz. Also, find the average power delivered by the source. Find the current and unknown voltages in the circuit shown. A voltage of a 100 angle 30 degrees volts is applied across a resistor and inductor that are in series. If the resistor RMS voltage drop is 40 volts, what is the inductor voltage phasor? In a phasor domain circuit, 220 angle 30 degrees volts is applied across two series components, one of which is 20 ohm resistor and the other of which is a coil with an impedance as given. Use current to find the individual component voltage drops. I'll repeat the problem using voltage division. A phasor domain circuit has this voltage applied across three series connected components having impedance as given. Use voltage division to find the voltage drop V across the component with the impedance given. Use voltage division to find VR, VL, VC in the circuit shown. Use voltage division to find the voltage V in the circuit shown in the figure. Find the current in the circuit shown. Use voltage division twice to find V1 in the circuit shown. Derive expressions for the conductance and susceptance of an admittance in terms of the resistance and reactance of the corresponding impedance. The impedance of a circuit has 2 ohms of resistance and 4 ohms of reactance. What are the conductance and susceptance of the admittance? Find the total admittances in polar form of a 0.2 microfarad capacitor and a parallel 5.1 resistor at frequencies A, B, and C Hertz. A 200 ohm resistor, a 1 microfarad capacitor, and a 75 millihenry inductor are in parallel. Find the total admittance in polar form at 400 Hertz. Also, draw the admittance diagram and the admittance triangle. A 100 ohm resistor, a 1 millihenry inductor, and a 0.1 microfarad capacitor are in parallel. Find the total admittance in polar form at radian frequencies of A, B, and C kiloradians per second. 3 components in parallel have a total admittance of YT as given. If the admittances of the 2 components are these, what is the admittance Y3 of the third component? What is the total impedance of 3 parallel components that have impedances as given? Find the simplest parallel circuit that has the same impedance at 400 Hz as the series combination of a 300 ohm resistor, a 0.25 Henry inductor, and a 1 microfarad capacitor. A load has a voltage of as given and a current as given, both at 2 kilohertz. Find the 2-element parallel circuit that the load can be. As always, assume associated references because there is no statement to the contrary. A 0.5 ohm resistor is in parallel with a 10 millihenry inductor. At what radian frequency do the circuit voltage and current have a phase angle difference of 40 degrees? A resistor in a parallel 1 microfarad capacitor draws 0.48 amps when 120 volt at 400 Hz is applied. Find the admittance in polar form. Capacitors are sometimes connected in parallel with inductive industrial loads to increase the current drawn from the source without affecting the load current. To verify this concept, consider connecting a capacitor across a coil that has a 10 millihenry of inductance and 2 ohms of resistance, and that is energized by a 60 Hertz 120 volt source. What is the capacitance required to make the source current a minimum? And what is the decrease in the current? Find the total impedance ZT of the circuit shown. Find the input admittance at 50 kiloradians per second of the circuit shown. Find I in and IL for the circuit. A current as given flows into 4 parallel branches that have admittances as given. Use current division to find the current I in this branch. Of course, since there is no statement to the contrary, blah, blah, blah. Use current division to find IL for the circuit shown. Use current division to find IL for the circuit shown. Use current division twice to find the current IL for the circuit shown. Determine VO and IO in the circuit. Find VO and IO in the circuit. Calculate VO in the circuit. Find IO in the circuit. Determine VO in the circuit. Supplementary problems. A 0.5 microfarad capacitor and a 2 kilo ohm resistor are in series. Find the total impedance in polar form at A, B, and C hertz. A 300 ohm resistor, a 1 Henry inductor, and a 1 microfarad capacitor are in series. Find the total impedance in polar form and whether the circuit is inductive or capacitive at A, B, and C radians per second. A capacitor and a resistor in series have an impedance of as given at 400 hertz. Find the capacitance and resistance. A load has a voltage as given and a current as given at a frequency of 60 hertz. Find the two element series circuit that the load can be. Two circuit elements in series draw a current of as given in response to an applied voltage of this. Find the two elements. A 100 ohm resistor is in series with a 120 millihenry inductor. At what frequency do the circuit voltage and current have a phase angle difference at 35 degrees? A 750 ohm resistor is in series with a 0.1 microfarad capacitor. At what frequency does the total impedance have a magnitude of 1000 ohms? Find the total impedance in polar form of the 3 series connected components that have impedances of this, this, and this. What resistor in series with a 2 Henry inductor limits the current to 120 milliamps when 120 volts at 60 hertz is applied? Two circuit elements in series draw a current of 20 of this in response to an applied voltage of this. Find the two elements. Find the input impedance at 20 kiloradians per second for the circuit shown. A 300 volt source is connected in series with 3 components, 2 of which have impedances as given. Find the impedance of the third component if the current that flows is 5 amps and it lags the source voltage by 20 degrees. Find the total impedance of 2 parallel components that have identical impedances. What is the total impedance of 2 parallel components that have impedances as given? A 120 millihenry coil with a 30 ohm winding resistance is in parallel with 20 ohm resistor. What series resistor and inductor produce the same impedance at 60 hertz as this parallel combination? A 2 millihenry coil with a 10 ohm winding resistance is in parallel with a 10 microfarad capacitor. What 2 series circuit elements have the same impedance at 8 kiloradians per second? For the circuit shown in figure 1230, find I, VR, and VC and the corresponding sinusoidal quantities if the frequency is 50 hertz. Also find the average power delivered by the source. A voltage source of 300 as given, a 2 ohm resistor and a 1 Henry inductor and a 1 microfarad capacitor are in series. Find the current out of the positive terminal of the source. Also find the resistor, inductor, and capacitor voltage drops. A voltage that has a phasor as given is applied across a resistor and capacitor that are in series. If the capacitor RMS voltage is 120 volts, what is the resistor voltage phasor? A phasor domain circuit has voltage applied across 2 components, a 30 ohm resistor and a coil that has an impedance as given. Find the following drops across the resistor and the coil. Find the voltage drops across the resistor and the coil. A voltage source of this voltage and a 200 ohm resistor and a 10 microfarad capacitor are in series. Find the resistor and capacitor voltage drops. Repeat the problem with an added series 1 Henry inductor. Also find the inductor voltage. A phasor domain circuit has this voltage applied across 3 series connected components that have impedances as given. Find the component voltage drops. What is the current I for the circuit shown? Use voltage division twice to find V in the circuit shown. Derive expressions for the resistance and reactance of an impedance in terms of the conductance and susceptance of the corresponding admittance. Find the total admittance in polar form of a 1 microfarad capacitor and a parallel 3.6 kilo ohm resistor at A, B, and C hertz. A 1 kilo ohm resistor, a 1 Henry inductor, and a 1 microfarad capacitor are in parallel. Find the total admittance in polar form at A, B, and C radians per second. An inductor and a parallel resistor have an admittance as given at 400 Hz. What are the inductance and resistance? Find the simplest series circuit that has the same total impedance at 400 Hz as the parallel arrangement of a 620 ohm resistor, a 0.5 Henry inductor, and a 0.5 microfarad capacitor. A load has a voltage as given and a current as given. What two element parallel circuit can this load be at 400 Hz? A resistor and a parallel 0.5 microfarad capacitor draw 50 milliamps when 120 volts at 60 Hz is applied. What is the total admittance in polar form and what is the resistance of the resistor? What two circuit elements in parallel have an admittance of this at 60 Hz? What two circuit elements in parallel have this admittance at 400 Hz? 3 circuit elements in parallel have an admittance as given at a frequency of 2 kHz. If one is a 60 millihenry inductor, what are the 2 other elements? A 2 kilo ohm resistor in parallel with a 1 microfarad capacitor. At what frequency does the total admittance have an angle of 40 degrees? A resistor and a parallel 120 millihenry inductor draws 3 amps when 100 volts at 60 Hz is applied. What is the total admittance? A certain industrial load has an impedance as given at a frequency of 60 Hz. What capacitor connected in parallel with this load causes the angle of the total impedance to decrease to 15 degrees? Also, if the load voltage is 120 volts, what is the decrease in line current produced by adding the capacitor? Find the admittance Y of the circuit shown. Find the input admittance at 1 kiloradians per second of the circuit shown. Repeat the problem with for a radian frequency of 1 megaradians per second. A current as given flows into 3 parallel branches that have impedances of 200, J10, and negative J10 ohms. Find the current in the J10 ohm branch. A current of this flows into the parallel combination of a 100 ohm resistor and a 25 microfarad capacitor. Find the capacitor current. A current of this flows into 3 parallel branches that have impedances as given. What is the current in this branch? Use current division twice to find the current for the circuit shown. Calculate I0 in the circuit. Find I0 in the circuit. Obtain VO and IO in the circuit. Calculate VO in the circuit. Determine VO and IO in the circuit and obtain VO in the circuit. Chapter 13, Mesh, Loop, Nodal, and P-Spice Analysis of AC Circuits. Introduction, Source Transformations, Mesh and Loop Analysis, Nodal Analysis, P-Spice AC Analysis. Solve problems. Perform a source transformation on the circuit shown. Perform a source transformation on the circuit shown. Perform a source transformation on the circuit shown. And perform a source transformation on the circuit shown. Assume that the following equations are mesh equations for a circuit that does not have any current sources or dependent sources. Find the quantities that go in the blanks. Find the voltages across the impedances in the circuit shown, and transform the voltage source and this component to an equivalent current source and again find the voltages. Compare the results. Find the mesh currents. Find the mesh currents for the circuit shown. Solve for the mesh currents I1 and I2 in the circuit shown. Use loop analysis to find the current down through the 4 ohm resistor in the circuit shown. Find the mesh currents for the circuit shown. Use loop analysis to solve for the current flowing down through the 5 ohm resistor in the circuit shown. Use mesh analysis to solve for the currents in the circuit. Show a circuit that corresponds to the following mesh equations. Use loop analysis to solve for the current flowing to the right through the 6 ohm resistor in the circuit shown. Solve for the node voltages in the circuit shown. Find the node voltages in the circuit shown. Use nodal analysis to find V for the circuit shown. Find the node voltages in the circuit shown. Calculate the node voltages in the circuit. Show a circuit corresponding to the nodal equations. For the circuit shown, which contains a transistor model, first find V as a function of I, then find V as a numerical value. Solve for I in the circuit shown. Use PSpice to obtain the mesh currents in the circuit given. Calculate VO in the circuit. Repeat the problem using PSpice. Use PSpice to determine VO in the circuit. Find VO in the circuit. Repeat the problem using PSpice. Supplementary problems. A 30 ohm resistor and a 0.1 Henry inductor are in series with a voltage source that produces a voltage of 120 blah blah blah. Find the components for the corresponding phasor domain current source transformation. A voltage source is in series with a 6 ohm resistor and the parallel combination of a 10 ohm resistor and an inductor with a reactance of 8 ohms. Find the equivalent current source circuit. A voltage source is in series with the parallel arrangement of an inductor that has a reactance of 100 ohms and a capacitor that has a reactance of minus 100 ohms. Find the current source equivalent circuit. Find the voltage source circuit equivalent of the parallel arrangement of a current source, a 60 ohm resistor, and an inductor with an 80 ohm reactance. A current source is in parallel with the series arrangement of an inductor that has a reactance of 100 ohms and a capacitor that has a reactance of minus 100 ohms. Find the equivalent voltage source circuit. In the circuit shown, find currents I1 and I2, then do source transformation on the current source and parallel impedance and find the currents in the impedances, and then compare. Find the mesh currents in the circuit shown. Find I in the circuit shown. Find the mesh currents. Find the mesh currents. Use loop analysis to solve for the current that flows down in the 10 ohm resistor in the circuit shown. Use mesh analysis to find current I in the circuit. Use loop analysis to find current flowing through the capacitor in the circuit. Find the current I in the circuit. For the circuit shown, use loop analysis to find current flowing down through the capacitor that has the reactance of minus J2 ohms. Use loop analysis to find I in the circuit shown. Rework problem 1344 with all impedances doubled. Find the node voltages in the circuit shown. Find the node voltages in the circuit. Solve for the node voltages in the circuit. Find the node voltages in the circuit. Solve for the node voltages in the circuit. For the circuit shown, find V as a function of I and then find V as a numerical value. Solve for I in the circuit shown. Okay. And then in problems 1353 through 1358, given the specified PSpice circuit files, determine the output phasor voltages or currents without using PSpice. Wow. Chapter 14, AC equivalent circuits. AC equivalent circuits, network theorems, and bridge circuits. Introduction, Thevenin's and Norton's theorems, maximum power transfer theorem, superposition theorem, AC Y delta and delta Y transformations, AC bridge circuits, solve problems, find Thevenin impedance, Thevenin voltage, and Norton current for the Thevenin and Norton equivalents of the circuit external to the load impedance ZL in the circuit shown. If in the circuit shown the load is a resistor with resistance R, what value of R causes a 0.1 amp RMS current to flow through the load? Find the Thevenin impedance, the Thevenin voltage, and the Norton current for the Thevenin and Norton equivalents of the circuit shown in the figure. Find the Thevenin impedance, Thevenin voltage, and Norton current for the Thevenin and Norton equivalents of the circuit shown. And again for this circuit, and again for this circuit. Okay, and we're going to find the Thevenin impedance and the Norton current for the circuit shown, and then the Thevenin voltage and the impedance for the circuit shown, and then using Thevenin or Norton's theorem, find the current in the bridge circuit shown, find the current for the circuit shown, find the output impedance of the circuit to the left of the terminals AB for the circuit shown, find the Thevenin impedance and Norton current for the Norton equivalent of the circuit shown. Find the Thevenin impedance and the Norton current for the Norton equivalent of the transistor circuit. Use P-Spice to obtain the Thevenin equivalent of the circuit. What is the maximum average power that can be drawn from an AC generator that has an internal impedance as given and an RMS open circuit voltage of 12.5 kilovolts? Do not be concerned about whether the generator power rating may be exceeded. A signal generator operating at 2 MHz has an RMS open circuit voltage of 0.5 volts and an internal impedance as given. If it energizes a capacitor and parallel resistor, find the capacitance and resistance of these components for maximum average power absorption by the resistor. Also find this power. For the circuit shown in the figure, what load impedance ZL absorbs maximum average power, and what is this power? In the circuit shown, find R and L for maximum average power absorption by the parallel resistor and capacitor load, and also find this power. Use superposition to find the voltage in the circuit shown. Use superposition to find the current in the circuit shown. Use superposition to find the current for the circuit shown if the voltage of the voltage source is changed to this. Although superposition does not usually apply to power calculation, it does apply to the calculation of average power absorbed when all sources are sinusoids of different frequencies. A DC source can be considered to be a sinusoidal source of zero frequency. Using this fact to find the average power absorbed by the 5 ohm resistor in the circuit shown. Use superposition to find voltage in the circuit. Transform the delta shown in the figure to the Y in the figure, blah, blah, blah. Transform the Y shown to the delta shown. Using delta to Y transformation, find I for the circuit shown. Find the current I for the circuit shown. Assume that the bridge circuit of the figure is balanced for these impedances and for the source frequency of 2 kilohertz. If branch ZX consists of 2 components in series, what are they? The bridge circuit shown in the figure is a capacitance comparison bridge that is used for measuring the capacitance Cx of a capacitor and any resistance Rx inherent to the capacitor or in series with it. The bridge has a standard capacitor, the capacitance Cs of which is known. Find Rx and Cx if the bridge is in balance for the resistors and the capacitors as given. and a source radiant frequency of 1 kiloradians per second. For the capacitance comparison bridge shown in figure, derive general formulas for Rx and Cx in terms of the other bridge components. The bridge circuit shown in the figure, called the Maxwell bridge, is used for measuring the inductance and resistance of a coil in terms of a capacitance standard. Find Lx and Rx if the bridge is in balance for the resistors and the capacitors. Supplementary problems. Find the Thevenin voltage and the Thevenin impedance for the Thevenin equivalent of the circuit shown. What resistor will draw an 8 amp RMS current when connected across terminals A, B of the circuit shown. Find the Norton current and the Thevenin impedance for the Norton equivalent of the circuit shown. Find the Thevenin voltage and the Thevenin impedance for the Thevenin equivalent of the circuit shown. Find the Norton current and the Thevenin impedance for the Norton equivalent of the circuit shown. Find the Thevenin voltage and the Thevenin impedance for the Thevenin equivalent of the circuit shown. Find the Thevenin voltage and the Thevenin impedance for the Thevenin equivalent of the circuit shown. And again, and then what resistor will draw 2 amp RMS current when connected across terminals A, B of the circuit shown. Using Thevenin's or Norton's theorems, find I for the bridge circuit shown in the figure. Find I for the bridge circuit shown. Find the output impedance of the circuit shown. Find the output impedance of the circuit shown. Find Thevenin voltage and Thevenin impedance for the Thevenin equivalent in the circuit shown in the figure. Reverse the I reference direction. Have it up instead of down, and find the Norton current and the Thevenin impedance for the Norton equivalent circuit. Find the output impedance at 10 to the 4 radians per second of the circuit shown. Use P-Spice to obtain the Thevenin equivalent at the A and B terminals of the phasor domain circuit corresponding to the time domain circuit of figure 1446. What is the maximum average power that can be drawn from an AC generator that has an internal impedance as given and an open circuit voltage of 25 kilovolt RMS? A signal generator operating at 5 megahertz has an RMS short circuit current of 10 milliamps and an internal impedance as given. If it energizes a capacitor and a parallel resistor, find the capacitance and resistance for a maximum average power absorption by the resistor. Also find this power. For the circuit shown, what ZL, which is what load impedance, draws maximum average power, and what is this power? In the circuit shown in figure 1447, move the negative J8 ohm impedance from in series with the current source to in parallel with it. Find the load impedance that absorbs maximum average power and find this power. Use superposition to find I for the circuit shown. For the circuit shown in the figure, find the average power dissipated in the 3 ohm resistor using superposition and then without using superposition. Repeat this with 10 degrees phase angle change to 40 degrees for the 1 voltage source. The problem illustrates the fact that superposition can be used to find the average power absorbed by a resistor from 2 sources of the same frequency only if these sources produce resistor currents that have a 90 degrees difference in phase angle. Find V for the circuit shown. Find the average power dissipated in the 5 ohm resistor of the circuit shown. Find I for the circuit shown. Find the average power absorbed by the 200 ohm resistor in the circuit shown. Transform the T shown in figure to the product, or pi, capital Pi. Okay. Transform the capital Pi shown in the figure to the T in the figure. Oh, I see. The T and the pi. Yeah, right. It's kind of like the delta and triangle. Using a delta Y transformation, find I for the current for the circuit shown. Using a delta Y transformation, find I for the circuit shown. Assume that the bridge circuit shown is balanced for these impedances. and for a source frequency of 5 kilohertz. If branch ZX consists of two components in parallel, what are they? Find CX and RX for the capacitor comparison bridge shown. If this bridge is balanced for these resistances and this capacitance. Find LX, RX for the Maxwell bridge shown in the figure, if this bridge is balanced for these resistances and this capacitance. Chapter 15, Power in AC Circuits. Introduction, circuit power absorption, watt meters, reactive power, complex power and apparent power, power factor correction. Solve problems. The instantaneous power absorbed by a circuit is given. Find the maximum, minimum, average absorbed powers. With a V as given, applied, a circuit draws current as given. Find the power factor and also the average, maximum, and minimum absorbed powers. For each following load, voltage, and current pair, find the corresponding power factor and average power absorbed. Find the power factor of a circuit that absorbs 1.5 kilowatts for a 120 volt input voltage and a 16 amp current. What is the power factor of a fully loaded 10 horsepower induction motor that operates at 80% efficiency while drawing 28 amps from a 480 volt line? Find the power absorbed by a load of this when 42 volts is applied. What power is absorbed by a circuit that has an input admittance of 0.4 plus J 0.5 Siemens and an output current of 30 amps? A resistor in parallel with a capacitor absorbs 20 watts when the combination is connected to a 240 volt 60 hertz source. If the power factor is 0.7 leading, what are the resistance and capacitance? A resistor in series with a capacitor absorbs 10 watts when the combination is connected to a 120 volt 400 hertz source. If the power factor is 0.6 leading, what are the resistance and capacitance? If a coil draws half an amp from a 120 volt 60 hertz source at 0.7 lagging power factor, what are the coil resistance and inductance? A resistor and parallel capacitor draws 0.2 amps from a 24 volt 400 hertz source at a 0.8 leading power factor. Find the resistance and capacitance. It's going to take a break. All right. Operating at maximum capacity, a 12,470 volt alternator supplies 35 megawatts at a 0.7 lagging power factor. What is the maximum real power that the alternator can deliver? An induction motor delivers 50 horsepower while operating at 80% efficiency from a 480 volt lines. If the power factor is 0.6, what current does the motor draw? If the power factor is 0.9 instead, what current does this motor draw? For the circuit shown in figure 15.4, find the wattmeter reading when the plus or minus terminal of the potential coil is connected to node A and also when it is connected to node B. In the circuit shown in the figure, find the total power absorbed by the three resistors. Then find the sum of the readings of the two wattmeters and compare results. What is the reactive power factor of an inductive load that has an apparent power input of 50 kilovolt amps while absorbing 30 kilowatts? With voltages given applied, a circuit draws current of this. What is the reactive factor and what is the reactive power absorbed? What is the reactive factor of a circuit that has an input impedance as given? Also, what reactive power does the circuit absorb when the current is 5 amps? What is the reactive factor of a circuit that has an impedance as given? What is the reactive power absorbed with 240 volts applied? when 3 amps flows through a circuit with an input in admittance of 0.4 plus J 0.5 Siemens, what active power does the circuit consume? Two circuit elements in series consume 60 VAR when connected to 120 volt 60 hertz source. If the reactive power if the reactive factor is 0.6, what are the two components and what are their values? What resistor and capacitor in parallel present the same load to a 480 volt 60 hertz source as a fully loaded 20 horsepower synchronous motor that operates at 75% efficiency and a 0.8 leading power factor? A 120 millihenry inductor is energized by 120 volts at 60 hertz. Find the average peak and reactive powers absorbed. What are the power components resulting from a 4 amp current flowing into a load as given? In other words, what are the complex real, reactive, and apparent powers of the load? Find the power components of an induction motor that delivers 5 horsepower while operating at an 85% efficiency and a 0.8 lagging power factor. Find the power components of a load that draws this many amps with this voltage applied. A load connected across a 1000 or a 12,470 volt line draws 20 amps at 0.75 lagging power factor. Find the load impedance and the power components. A 20 microfarad capacitor and a parallel 200 ohm resistor draw 4 amps at 60 hertz. Find the power components. A fully loaded 10 horsepower induction motor operates from a 480 volt 60 hertz line at an efficiency of 85% and a 0.8 lagging power factor. Find the overall power factor when a 33.3 microfarad capacitor is placed in parallel with the motor. A 240 volt source energizes the parallel combination of a purely resistive 8 kilowatt heater and an induction motor that draws 7 kilovolt amps at 0.8 lagging power factor. Find the overall load power factor and also the current from the source. A 480 volt source energizes 2 loads in parallel, supplying 2 kVA at a 0.5 lagging power factor to one load and a 4 kVA at 0.6 leading power factor to the other load. Find the source current and also the total impedance of the combination. 3 loads are connected across a 277 volt line. One is a fully loaded 5 horsepower induction motor operating at 75% efficiency and a 0.7 lagging power factor. Another is a fully loaded 7 horsepower synchronous motor operating at 80% efficiency and a 0.4 leading power factor. The third is a 5 kilowatt resistive heater. Find the total line current and the overall power factor. In the circuit shown in the figure, load 1 absorbs 2.4 kilowatts and 1.8 kVAR. Load 2 absorbs 1.3 kilowatts and 2.6 kVAR. And load 3 absorbs 1 kilowatt and generates 1.2 kVAR. Find the total power components and the source current and the impedance of each load. A load that absorbs 100 kilowatts at 0.7 lagging power factor has capacitors placed across it to produce an overall power factor of 0.9 lagging. The line voltage is 480 volts. How much reactive power must the capacitors produce, and what is the resulting decrease in line current? A synchronous motor that draws 20 kilowatts is in parallel with an induction motor that draws 50 kilowatts at a lagging power factor of 0.7. If the synchronous motor is operated at a leading power factor, how much reactive power must it provide to cause the overall power factor to be 0.9 lagging, and what is its power factor? A factory draws 100 amps at 0.7 lagging power factor from a 12,470 volt 60 hertz line. What capacitor placed across the line at the input to the factory increases the overall power factor to unity? Also, what are the final currents for the factory, capacitor, and line? A 240 volt 60 hertz source energizes a load as given. What capacitor in parallel with this load produces an overall power factor of 0.95 lagging? At 60 hertz, what is the power factor of the circuit shown? What capacitor connected across the input terminals causes the overall power factor to be unity? What capacitor causes the overall power factor to be 0.85 lagging? An induction motor draws 50 kilowatts at a 0.6 lagging power factor from 480 volt 60 hertz source. What parallel capacitor will increase the overall power factor to 0.9 lagging? What is the resulting decrease in input current? A factory draws 30 megavolt amps at a 0.7 lagging power factor from a 12,470 volt 60 hertz line. Find the capacitance of the parallel capacitors required to improve the power factor to 0.85 lagging. Also, find the resulting decrease in line current. A 20 megawatt industrial load supplied from a 12,470 volt 60 hertz line has its power factor improved to 0.9 lagging by the addition of 230 microfarad bank of capacitors. Find the power factor of the original load. A 480 volt 60 hertz source energizes a load consisting of an induction motor and a synchronous motor. The induction motor draws 50 kilowatts at a 0.65 lagging power factor, and the synchronous motor draws 10 kilowatt at 0.6 leading power factor. Find the capacitance of the parallel capacitor required to produce an overall power factor of 0.9 lagging. Supplementary problems. The instantaneous power absorbed by a circuit is given. Find the maximum, minimum, and average power absorbed. With this voltage applied, a circuit draws this current. Find the power factor and the maximum, minimum, and average powers absorbed. For each following load, find the current pair, find the corresponding power factor and average power absorbed. Find the power factor of a fully loaded 5 horsepower induction motor that operates at 85% efficiency while drawing 15 amps from a 480 volt line. What is the power factor of a circuit that has an input impedance as given? Also, what is the power absorbed when 50 volts is applied? If a circuit has an input admittance as given and an applied voltage of 180 volts, what is the power factor and the power absorbed? A resistor in parallel with an inductor absorbs 25 watts when the combination is connected to a 120 volt 60 hertz source. If the total current is 0.3 amps, what are the resistance and inductance? A coil absorbs 20 watt when connected to a 240 volt 400 hertz source. If the current is 0.2 amps, find the resistance and inductance of the coil. A resistor and a series capacitor draw 1 amp from a 120 volt 60 hertz source at a 0.6 leading power factor. Find the resistance and capacitance. A resistor and parallel capacitor draw 0.6 amp from a 120 volt 400 hertz source at 0.7 leading power factor. Find the resistance and capacitance. A 100 kilowatt load operates at 0.6 lagging power factor from a 480 volt 60 hertz line. What current does the load draw? What current does the load draw if it operates at unity power factor instead? A fully loaded 100 horsepower induction motor operates at 85% efficiency from a 480 volt line. If the power factor is 0.65 lagging, what current does the motor draw? If the power factor is 0.9 lagging instead, what current does this motor draw? Find the wattmeter reading for the circuit shown. Find each wattmeter reading for the circuit shown. With the voltage applied, a circuit draws this current. What is the reactive factor and what is the reactive power absorbed? With this voltage applied, a circuit draws this current. What is the reactive factor and what is the reactive power absorbed? And what is the reactive factor of a circuit that has an input impedance as given? What reactive power does the circuit absorb when the current is 4 amps? What is the reactive power factor of a circuit that has an input impedance as given? What is the reactive power absorbed when 480 volts is applied? When 120 volts is applied across a circuit with an input admittance as given, what reactive power does the circuit absorb? When 4.1 amps flows into a circuit with an input impedance as given, what reactive power does the circuit absorb? A load consumes 500 VAR when energized from a 240 volt source. If the reactive power factor is 0.35, what current does the load draw and what is the load impedance? Two circuit elements in parallel consume 90 VAR when connected to a 120 volt 60 Hz source. If the reactive factor is 0.8, what are the two components and what are their values? Two circuit elements in series consume negative 80 VAR when connected to a 240 volt 60 Hz source. If the reactive factor is minus 0.7, what are the two components and what are their values? A 300 milliamp 60 Hertz current flows through a 10 microfarad capacitor. Find the average peak and reactive powers absorbed. What are the power components resulting from a 3.6 amp current flowing through a load as given? Find the power components of a fully loaded 10 horsepower synchronous motor operating at 87% efficiency and a 0.7 leading power factor. A load draws 3 amps with 75 volts applied. If the load power factor is 0.6 lagging, find the power components of the load. Find the power components of a load that draws this many amps with this many volts applied. A 120 millihenry inductor and a parallel 30 ohm resistor draw 6.1 amps at 60 Hertz. Find the power components. A fully loaded 15 horsepower induction motor operates from a 480 volt 60 Hz line at an efficiency of 83% and a 0.7 lagging power factor. Find the overall power factor when a 75 microfarad capacitor is placed in parallel with the motor. Two loads are connected in parallel across a 277 volt line. One is a fully loaded 15 horsepower induction motor that operates at an 80% efficiency and a 0.7 lagging power factor. The other is a 5 kilowatt resistive heater. Find the overall power factor and line current. Two loads are connected in parallel across a 12,470 volt line. One load takes 23 kVA at a 0.75 lagging power factor, and the other takes 10 kVA at a 0.6 leading power factor. Find the total line current and also the impedance of the combination. Three loads are connected across a 480 volt line. One is a fully loaded 10 horsepower induction motor operating at 80% efficiency and a 0.6 lagging power factor. Another is a fully loaded 5 horsepower synchronous motor operating at 75% efficiency and a 0.6 leading power factor. The third is a 7 kilowatt resistive heater. Find the total line current and the overall power factor. In the circuit shown in the figure, load 1 absorbs 6.3 kilowatts and 9.27 kVAR, and load 2 absorbs 5.26 kilowatts and generates 2.17 kVAR. Find the total power components, the source voltage, V, and the impedance of each load. How much reactive power must be supplied by parallel capacitors to a 50 kVA load with a 0.65 lagging power factor to increase the overall power factor to 0.85 lagging? An electric motor delivers 50 horsepower while operating from a 480 volt line at an 83% efficiency and a 0.65 lagging power factor. If it is paralleled with a capacitor that increases the overall power factor to 0.9 lagging, what is the decrease in line current? A load energized from a 480 volt 60 Hz line has a power factor of 0.6 lagging. If placing a 100 microfarad capacitor across the line raises the overall power factor to 0.85 lagging, find the real power of the load and the decrease in line current. A factory draws 90 amps at 0.75 lagging power factor from a 25,000 volt 60 Hz line. Find the capacitance of a parallel capacitor that will increase the overall power factor to 0.9 lagging. A fully loaded 75 horsepower induction motor operates from a 480 volt 60 Hz line at an 80% efficiency and a 0.65 lagging power factor. The power factor is to be raised to 0.9 lagging by placing a capacitor across the motor terminals. Find the capacitance required and the resulting decrease in line current. A load as given is connected to a 480 volt 60 Hz source. What capacitor connected in parallel with the load will produce an overall power factor of 0.9 lagging? At 400 Hz, what is the power factor of the circuit shown? What capacitor connected across the input terminals causes the overall power factor to be 0.9 lagging? For a load energized by a 277 volt 60 Hz source, an added parallel 5 microfarad capacitor improves the power factor from 0.65 lagging to 0.9 lagging. What is the source current, both before and after the capacitor is added? All right, well, we're nearly there. This is chapter 16, Transformers. Introduction, right-hand rule, dot convention, the ideal transformer, the air core transformer, the auto transformer, P-Spice and transformers. Solved problems. For the winding shown in the figure, what is the direction of flux produced in the core by current flowing into terminal A? Supply the missing dots for the transformers shown in the figure. What is the turns ratio of a transformer that has a 684 turn primary winding and a 36 turn secondary winding? Find the turns ratio of the transformer that transforms the 12,470 volts of a power line to the 240 volts supplied to a house. What are the full load primary and secondary currents of a 25,000/240 volt 500 kVA transformer? A power transformer with a voltage rating of 12,500/240 volts has a primary current rating of 50 amps. Find the transformer kVA rating and the secondary current rating of the 240 volt if the 240 volts is the secondary voltage rating. A transformer has a 500 turn winding linked by flux changing at a rate of 0.4 webers per second. Find the induced voltage. An iron core transformer has 400 primary turns and 100 secondary turns. If the applied primary voltage is 240 volts RMS at 60 Hz, find the secondary RMS voltage and the peak magnetic flux. If a 50 turn transformer winding has 120 volts RMS applied voltage, and if the peak coupling flux is 20 milliwebers, find the frequency of the applied voltage. An iron core transformer has 1,500 primary turns and 500 secondary turns. A 12 ohm resistor is connected across the secondary winding. Find the resistor voltage when the primary current is 5 amps. The output stage of an audio system has an output resistance of 2 kiloohms. An output transformer provides resistance matching with a 6 ohm speaker. If this transformer has 400 primary turns, how many secondary turns does it have? In the circuit shown in the figure, find the resistance for maximum power absorption. Also find current for resistance of 3 ohms. Finally, determine if connecting a conductor between terminals D and F would change these results. Find I1, I2, and I3 for the circuit shown. The transformers are ideal. Find I1 and I2 for the circuit shown. Find I1 and I2 for the circuit shown. And again, pardon me, find the voltage for the circuit shown. Use PSpice to determine the voltage in the circuit of the figure. Find the current in the circuit. Repeat the problem using PSpice. Determine the branch currents I1, I2, and I3 in the circuit. Repeat the problem using PSpice. An air core transformer has primary and secondary currents as given. Blah, blah, blah. Find phi M2 M blah, 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 blah. Okay. What is the greatest mutual inductance that an air core transformer can have if its self-inductances are 0.3 and 0.7 Henry? For each of the following, find the missing quantity. If either self-inductance, mutual inductance, or for each of the following, find the missing quantity, either self-inductance, mutual inductance, or coefficient of coupling. An air core transformer has an open circuited secondary winding with 50 volts across it when the primary current is 30 milliamps at 3 kilohertz. If the primary inductance is 0.3 henries, find the primary voltage and the mutual inductance. An air core transformer has an open circuit secondary with 80 volts across it when the primary carries a current of 0.4 amps and has a voltage of 120 volts at 60 hertz. What are the primary self-inductance and also the mutual inductance? Find the voltage across the open circuited secondary of an air core transformer when 35 volts at 400 hertz is applied to the primary. The transformer inductances are as given. Okay. An air core transformer with an open circuited secondary has inductances as given. M. I don't know what that is. It's in henries. So it's I should know. Find the primary and secondary voltages when the primary current is increasing at the rate of 0.5 kiloamps per second. The transformer with a short-circuited secondary has inductance L1, L2, and M. Find the short-circuit secondary current I2 when the primary current is I1 equals 0.5 amps at 60 hertz. When connected in series, two windings of an air core transformer have total inductances of 0.4 henries. With the reversal of the connections to one winding, though, the total inductance is 0.8 henries. Find the mutual inductance of the transformer. An air core transformer has 3 millihenries mutual inductance and a 5 millihenries secondary self-inductance. A 5 ohm resistor and a 100 microfarad capacitor are in series with the secondary winding. Find the impedance coupled into the primary for omega equals 1 kiloradians per second. A 1 kilo ohm resistor is connected across the secondary of a transformer for which L1, L2, and K are given. Find the resistor voltage when 250 volts at 400 hertz is applied to the primary. Find voltage for the circuit shown. Find current. Find the current I2 for the circuit shown. What is the total inductance of an air core transformer with its winding connected in parallel if both are at the same end and if the mutual inductance is 0.1 Henry and the self-inductances are 0.2 and 0.4 Henry? Find I2 for the circuit shown. Find V for the circuit shown. Then replace the 15 ohm resistor with an open circuit and find V again. Repeat the first part of problem 1638 using PSpice. Determine the mesh currents in the circuit. Repeat the problem using PSpice. What is the turns ratio of a 2-winding transformer that can be connected as an auto transformer of 500/350 kilovolts? Compare the winding currents of a fully loaded 277/120 volt 50 kVA 2-winding transformer and an auto transformer with the same rating. A 12,470/277 volt 50 kVA transformer is connected as an auto transformer. What is the kVA rating if the windings are connected as shown in figure 16.7a? And what is this rating if the windings are connected as shown in figure B? Find the three currents I1, 2, and 3 for the circuit shown. Supplementary problems. In the transformer shown, what is the direction of flux produced by the core by current flow into A terminal A, B terminal B, C terminal C, and D terminal D? Supply the missing dots for the transformer shown. What is the turns ratio of a power transformer that has 6.25 amp primary current at the same time that it has 50 amp secondary current? Find the turns ratio of a power transformer that transforms the 12,470 volts of a power line to the 480 volts used in a factory. What are the full load primary and secondary currents of a 7,200/120 volt 25 kVA power transformer? Assume that the 7,200 volt winding is the primary. A power transformer with a 13,200/480 volt rating has a fully loaded primary current rating of 152 amps. Find the transformer kVA rating and the full load secondary current rating if the 480 volts is a secondary voltage rating. A 7,200/120 volt 60 Hertz transformer has 1,620 turns on the primary. What is the peak rate of change of magnetic flux? Hint, remember that the voltage ratings are in RMS. An iron core transformer has 3,089 primary turns and 62 secondary turns. If the applied primary voltage is 13,800 volts RMS at 60 Hertz, find the secondary RMS voltage and the peak magnetic flux. If a 27-turn transformer winding has 120 volt RMS applied, and if the peak coupling flux is 20 milliwebers, what is the frequency of the applied voltage? An iron core transformer has 1,620 primary turns and 54 secondary turns. A 10 ohm resistor is connected across the secondary winding. Find the resistor voltage when the primary current is 0.1 of an amp. What should be the turns ratio of an output transformer that connects a 4 ohm speaker to an audio system that has an output resistance of 1,600 ohms? In the circuit shown in the figure, what should A and XC be for maximum average power absorption by the load impedance, and what is this power? Find I1, I2, and I3 in the circuit shown. Find voltage in the circuit shown. Find I1, I2, and I3 in the circuit shown. What is V in the circuit shown? Find I in the circuit shown. For the following PSpice circuit file, construct a corresponding phasor domain circuit diagram that contains an ideal transformer. Then use this diagram to calculate the answer that will appear in the output file when PSpice is run with this circuit file. Repeat the problem for the following PSpice circuit file. Repeat the problem for the following PSpice circuit file. An air core transformer has a primary current of 0.2 amps and a secondary current of 0.1 amps that produces fluxes of phi I1, 40 microwebers, blah, 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 blah. All right. What is the greatest possible mutual inductance of an air core transformer that has self-inductance of 120 and 90 millihenries? For each of the following, find the missing quantity, either self-inductance, mutual inductance, or coefficient of coupling. An air core transformer has an open-circuited secondary winding with 70 volts induced in it when the primary winding carries 0.3 amp current and has 120 volt 60 hertz voltage across it. What is the mutual inductance and primary self-inductance? An air core transformer with an open-circuited secondary has inductances of L1 equals 200 millihenries, L2 equals 320 millihenries, and M equals 130 millihenries. Find the primary and secondary voltages, reference positive at the dotted terminals when the primary current is increasing at the rate of 0.3 kiloamps per second into the dotted terminal of the primary winding. An air core transformer has inductances of L1, L2, and M. The primary current is increasing into the dotted primary terminal at a rate of 200 amps per second, and the secondary current is increasing into the dotted secondary terminal at a rate of 300 amps per second. What are the primary and secondary voltages referenced positive at the dotted terminals? An air core transformer with a shorted secondary has a 90 milliamp short circuit secondary current and a 150 milliamp primary current when 50 volts at 400 hertz is applied to the primary. If the mutual inductance is 110 millihenries, find the self-inductances. An air core transformer with a shorted secondary has inductances of L1, L2, and M. Find the winding currents when a primary voltage of 50 volts at 60 hertz is applied. A transformer has self-inductances of 1 and 0.6 Henry. One series connection of the windings results in a total inductance of 1 Henry. What is the coefficient of coupling? The transformer windings of a transformer are connected in series with dotted terminals adjacent. Find the total inductance of the series connected windings if L1, L2, and K are given. An air core transformer has an 80 millihenry mutual inductance and a 200 millihenry secondary self-inductance. A 2 kilo ohm resistor and a 100 millihenry inductor are in series with the secondary winding. Find the impedance coupled into the primary for omega equals 10 kiloradians per second. Find V in the circuit. A 6.8 kilo ohm resistor is connected across the secondary of a transformer having inductances of L1, L2, and M. What is the resistor current when 40 volts at 10 kiloradians per second is applied to the primary? Find I in the circuit. What is the total inductance of the parallel connected windings of an air core transformer if the dots are at opposite ends and if the mutual inductance is 100 millihenries and the self-inductances are 200 and 400 millihenries? Find I in the circuit, find V in the circuit, then switch the dot on one winding and find V again. In the circuit shown, place a short circuit across terminals A and B and find the short circuit current directed from terminal A to terminal B. For the circuit shown in figure, what load connected to terminals A and B absorbs maximum power and what is this power? Find the current in this circuit. Calculate the answer that will appear in the output file when SPICE is run with the following circuit file. Calculate the answer that will appear in the output file when PSpice is run with the following circuit file. Calculate the answer that will appear in this when the PSpice file is run. What is the turns ratio of a two-winding iron core transformer that can be connected as a 277/120 volt auto transformer? A 4800/240 volt 75 kVA power transformer is connected as an auto transformer. What is the kVA rating of the auto transformer for the connection shown in the figure? What is the kVA rating for the connection shown in the other figure? Find currents I1, I2, and I3 in this circuit. Chapter 17, Three-Phase Circuits. Introduction. Three-phase circuits are important because all electric power is generated and distributed three-phase. A three-phase circuit has an AC voltage generator, also called an alternator, that produces three sinusoidal voltages that are identical except for a phase angle difference of 120 degrees. The electric energy is transmitted over either 3 or 4 wires, more often called lines. Most of the three-phase circuits presented in this chapter are balanced. In them, 3 of the line currents are identical except for a phase angle of 120 degrees. Subscript notation. The polarities of voltages in three-phase circuits are designated by double subscripts, as in VAB. As may be recalled from Chapter 1, these subscripts identify the nodes that a voltage is across. Also, the order gives the voltage reference polarity. Specifically, the first subscript specifies the positively referenced node, and the second subscript the negatively referenced node. So VAB is a voltage drop from node A to node B. Also, VAB equals negative VBA. Double subscripts are also necessary for some current quantity symbols, as in IAB. These subscripts identify the nodes between which IAB flows, and the order of the subscript specifies the current reference direction. Specifically, the current reference direction is from the node of the first subscript to the node of the second subscript. So the current IAB has a reference direction from node A to node B. Also, IAB equals negative IBA. Figure 17.1 illustrates the subscript convention for IAB and also for VAB. Double subscript notation is also used for some impedances, as in ZAB. The subscripts identify the two nodes that the impedance is connected between, but the order of the subscripts has no significance. Consequently, ZAB equals ZBA. All right, three-phase voltage generation, generating windings connections, phase sequence, balanced Y circuit, balanced delta load, parallel loads, power, three-phase power measurements, unbalanced circuits, piecewise analysis of three-phase circuits, solve problems. What is the phase sequence of a balanced three-phase circuit in which VAN equals this voltage and VCN equals this voltage? What is VBN? What is the phase sequence of the balanced three-phase circuit in which blah, blah, blah? In a three-phase, three-wire circuit, find the phasor line currents to a balanced wire load in which each phase impedance is as given and the phase sequence is ABC. What is the phase sequence of a three-phase circuit in which VAB equals this and VBC equals this? Also, which line voltage has an angle that differs by 120 degrees from the angles of these voltages? A balanced three-phase Y load has one phasor voltage of VCN equals this if the phase sequence is VCB, ACB, and the line voltages VCA, VAB, and VBC. What are the phase voltages for a balanced three-phase Y load? If VBA is this, the phase sequence is ABC. A balanced three-phase, three-wire circuit with an ABC phase sequence has one line current of IB equals this. Find the other line currents. What is the IB line current in an unbalanced three-phase, three-wire circuit in which IA and IC are as given? A balanced Y load of 40 ohms resistors is connected to a 480 volt three-phase, three-wire source. Find the RMS line current. A balanced Y load of 50 as given impedances is energized by a 12,470 volt 3-phase 3-wire source. Find the RMS line current. Find the phasor line currents to a balanced wire load of impedances energized by a 3-phase source. One phase voltage is VBN and the phase sequence is ABC. In a 3-phase 3-wire circuit, find the phasor line currents to a balanced wire load for which the impedances and the voltages are given. The phase sequence is VBC, not VBC. ABC. What is the phase sequence of a balanced 3-phase circuit with a delta load in which two of the phase currents are IBA and ICB? What is IAC? Find the phase currents IBC, IAB, and ICA of a balanced 3-phase delta load to which one line current is IB. The phase sequence is ABC. A balanced 3-phase delta load has one phase current of IBA. The phase sequence is ACB. Find the other phase currents and also the phasor line currents. What are the phasor line currents to a balanced 3-phase delta load if one phase current is ICB and if the phase sequence is ABC? A 208 volt 3-phase circuit is a balanced delta load of 50 ohm resistors. Find the RMS line current. Find the phasor line currents to a balanced delta 3-phase load of impedances. The delta impedance is this if one phase voltage is VCB and if the phase sequence is ACB. A balanced delta load of impedances, Z delta, is connected to the Y-connected secondary of the 3-phase transformer. The phase sequence is ACB and VBN is as given. Find the phasor line currents and load phase currents. Find the RMS line voltage VL at the source of the circuit in figure 1714. As shown, the RMS load phase voltage is 100 volts and each line impedance is 2 plus J3 ohms. Find the RMS line voltage VL at the source of the circuit in the figure. As shown, the RMS line voltage at the load is 100 volts and each line impedance is 2 plus J3 ohms. A 480 volt 3-phase 3-wire circuit has two parallel connected balanced delta loads, one of 5 ohm resistors and the other of 20 ohm resistors. Find the total RMS line current. A 208 volt 3-phase 3-wire circuit has two parallel connected balanced wire loads, one of 6 ohm resistors and the other of 12 ohm resistors. Find the total RMS line current. A 600 volt 3-phase circuit has two parallel connected balanced delta loads, one of these with impedance as given and the other as given. Find the total RMS line current and also the total average absorbed power. A 208 volt 3-phase circuit has two parallel connected balanced loads, one of delta with this impedance and the other of Y with this impedance. Find the total RMS line current and also the total average absorbed power. A balanced Y with this impedance and a parallel connected balanced delta of this impedance are connected by 3 wires to the secondary of a 3-phase transformer. If VBC equals this voltage and the phase sequence is ABC, find the total phasor line currents. A balanced delta load of this impedance is connected by 3 wires with 4 ohms of resistance each to the secondary of a 3-phase transformer. If the line voltage is 480 volts at the secondary terminals, find the RMS line current. Find the average power absorbed by a balanced 3-phase load in an ABC circuit in which VCB and IB are given. 3-phase induction motor delivers 20 horsepower while operating at an 85% efficiency and at 0.8 lagging power factor from 480 volt lines. Find the RMS line current. A 3-phase induction motor delivers 100 horsepower while operating at an efficiency of 80% and a power factor of 0.75, lagging from 480 volt lines. The power factor is to be improved to a 0.9 lagging by inserting a delta bank of power factor correction capacitors. Determine the capacitance C delta required in each phase. In a 208 volt three-phase circuit, a balanced delta load absorbs 2 kilowatt at 0.8 leading power factor. Find delta impedance. Given that VAB is this in an ABC three-phase circuit, find the phasor line currents to a balanced load that absorbs 5 kilowatts at a 0.6 lagging power factor. A 480 volt three-phase circuit has two balanced load connected in parallel. One is a 5 kilowatt resistive heater and the other is an induction motor that delivers 15 horsepower while operating at an 80% efficiency and a 0.9 lagging power factor. Find the total RMS line current. If a three-phase, three-wire ABC circuit, IA is this, IB is this, and VAB is this, find the reading of a wattmeter connected with its current coil and line C and its potential coil across lines B and C. The plus or minus terminal of the current coil is toward the source and the plus or minus terminal of the potential coil is at line C. A balanced load of 25 ohm resistors is energized from a 480 volt three-phase, three-wire ABC source. Find the reading of a wattmeter connected with its current coil in line A and its potential coil across lines A and B. The plus or minus terminal of the current coil is towards the source and the plus or minus terminal of the potential coil is at line A. A balanced delta load of J40 ohm inductors is energized from a 208 volt ACB source. Find the reading of a wattmeter connected with its current coil in line B and its potential coil across lines B and C. The plus or minus terminal of the current coil is towards the source and the plus or minus terminal of the potential coil is at line B. A 240 volt ABC circuit has a balanced Y load as given. 2 wattmeters are connected for the 2 wattmeter method with current coils in lines A and C. Find the wattmeter readings. Also find these readings for an ACB phase sequence. A 208 volt circuit has a balanced delta load as given. 2 wattmeters are connected for the 2 wattmeter method with current coils in lines A and B. Find the wattmeter readings for an ABC phase sequence. A balanced Y load is connected to a 480 volt three-phase source. The 2 wattmeter method is used to measure the average power absorbed by the load. If the wattmeter readings are 5 kilowatts and 3 kilowatts, find the impedance of each arm of the load. 2 wattmeters both have readings of 3 kilowatts when connected for the 2 wattmeter method with current coils in lines A and B of a 600 volt ABC circuit having a balanced delta load. Find the delta phase impedance. 2 wattmeters are connected for the 2 wattmeter method with current coils in lines B and C of 480 volts ACB circuit that has a balanced delta load. If the wattmeter readings are 4 kilowatts and 2 kilowatts respectively, find the delta phase impedance Z delta. 2 wattmeters are connected for the 2 wattmeter method with current coils in lines A and C of a 240 volt ACB circuit that has a balanced Y load. Find the Y phase impedance if the 2 wattmeter readings are minus 1 kilowatts and 2 kilowatts respectively. A 240 volt ABC circuit has an unbalanced delta load consisting of resistors RAC equals 45 ohms, RBA equals 30 ohms, and RCB equals 40 ohms. 2 wattmeters are connected for the 2 wattmeter method with current coils in lines A and B. What are the wattmeter readings and the total average power absorbed? For a 4-wire ACB circuit in which the voltage is given, find the 4 phasor line currents to a Y load with ZA, ZB, and ZC as given. For an ABC circuit in which VAB is this, find the power phasor currents to a delta load of ZAB, ZBC, and ZCA ohms. Each line current, blah, blah, blah. Okay, in 3-wire ABC circuit in which VAB is given, find the phasor line currents to a Y load of ZA, ZB, ZC ohms. In the circuit of the figure, include the third voltage generator VCA and use P-Spice to obtain the 3 generator currents IAB, IBC, and ICA, as well as the line currents IA, IB, and IC. In the circuit shown in the figure, in which each line has an impedance of 5 plus J8, determine IA and IB. In a 3-wire ACB circuit in which one phase voltage at the Y-connected source is AN volts, determine the phasor line currents to a delta load in which ZAB, ZBC, and ZCA ohms. Each line has an impedance of 4 plus J7 ohms. Supplementary problems. What is the phase sequence of a Y-connected 3-phase alternator for which VAN volts and VBN volts? Also, what is VCN? Find the phase sequence of a balanced 3-phase circuit in which VAN and VCN are given. Also, find VBN. For a 3-phase 3-wire circuit, find the phasor line currents to a balanced wire load in which each phase impedance is this, and for which VCN is this. The phase sequence is ACB. Find the phase sequence of a 3-phase circuit in which VBA is this and VAC is this. Also find the third line voltage. What is the phase sequence of a 3-phase circuit for which VBN and VCB is given? A balanced Y load has one phase voltage of VBN volts. If the phase sequence is ABC, find the line voltages VAC, VCB, and VBA. What are the phase voltages for a balanced 3-phase Y load if VCA volts is this? The phase sequence is ACB. A balanced 3-wire ACB circuit has one line current of IC as given. Find the other line currents. Find the IC line current in an unbalanced 3-wire 3-phase circuit in which IA is this and IB is this. A balanced Y load of 100 ohm resistors is connected to a 208 volt 3-phase 3-wire source. Find the RMS line current. A balanced Y load of this impedance is connected to a 600 volt 3-phase 3-wire source. Find the RMS line current. Find the phasor line currents to a balanced Y load of given impedance. One phase voltage is VCN volts. The phase sequence is ACB, and there are only 3 wires. For a 3-phase 3-wire circuit, find the phasor line currents to a balanced 3-phase Y load of impedance as given if VAB is this and the phase sequence is ACB. Find the phase sequence of a 3-phase circuit in which 2 of the phase currents of a balanced delta load are IAB as given and IAC as given. Also find the third phase current. Find the phase currents IAC, ICB, and IBA of a balanced 3-phase delta load to which one line current is IA as given. The phase sequence is ACB. A balanced 3-phase delta load has one phase current of ICA as given. If the phase sequence is ABC, find the phasor line currents and the other phasor phase circuit currents. Find the phasor line currents to a balanced 3-phase delta load in which one phase current is IBA as given. The phase sequence is ACB. Find the RMS value of the line currents to a balanced delta load of 100 ohm resistors from a 480 volt 3-phase 3-wire source. Find the phasor line currents to a balanced 3-phase delta load of impedance as given if the phase sequence is ABC and if one phase voltage VCA is as given. A balanced delta load of this impedance is energized from the Y-connected secondary of a three-phase transformer for which VAN is this. If the phase sequence is ABC, find the phasor line and load currents. It's going to take a break. All right, well, we're almost there. A balanced Y load with impedances of 8 plus J6 ohms is connected to a three-phase source by 3 wires, each of which has 3 plus J4 ohms of impedance. The RMS load phase voltage is 50 volts. Find the RMS line voltage at the source. A balanced delta load with impedances of 15 minus J9 ohms is connected to a three-phase source by 3 wires, each of which has 2 plus J5 ohms of impedance. The RMS load phase voltage is 120 volts. Find the RMS line voltage at the source. A 600 volt three-phase 3-wire circuit has 2 parallel connected balanced delta loads, one of 30 ohm resistors and the other of 60 ohm resistors. Find the total RMS line current. A 480 volt three-phase 3-wire circuit has 2 parallel connected balanced Y loads, one of 40 ohm resistors and the other of 120 ohm resistors. Find the total RMS line current. A 480 volt three-phase circuit has 2 parallel connected balanced delta loads, one of this impedance and another of this impedance. Find the total RMS line current and the total average power absorbed. A 600 volt three-phase circuit has 2 parallel connected balanced loads, one a delta of this impedance and the other a Y of this impedance. Find the total RMS line current and the total average power absorbed. A balanced Y load of this impedance and a parallel connected balanced delta load of this impedance are connected by 3 wires to the secondary of a three-phase transformer. If VBA is this and the phase sequence is ACB, find the total phasor line currents. A balanced delta load of this impedance is connected to the secondary of a three-phase transformer by 3 wires that have 3 plus J4 ohms of impedance each. If the RMS line voltage is 480 volts at the secondary terminals, find the RMS line current. Find the average power absorbed by a balanced three-phase load in an ACB circuit in which one line voltage is VAC volts and one line current to the load is IB amps. A three-phase induction motor delivers 100 horsepower while operating at an 80% efficiency and a 0.7 lagging power factor from 600 volt lines. Find the RMS line current. A three-phase induction motor delivers 150 horsepower while operating at an efficiency of 75% and a power factor of 0.8 lagging from 480 volt lines. A Y bank of power factor correction capacitor is to be inserted to improve the overall power factor to 0.9 lagging. Determine the capacitance required per phase. In a 480 volt three-phase circuit, a balanced delta load absorbs 5 kilowatts at 0.7 lagging power factor. Find the delta phase impedance. Given that VAC is this in an ACB three-phase circuit, find the phasor line currents to a balanced load that absorbs 10 kilowatt at a 0.8 lagging power factor. A 600 volt three-phase circuit has 2 parallel connected balanced loads. One is a synchronous motor that delivers 30 horsepower while operating at an 85% efficiency and a 0.7 leading power factor. The other is an induction motor that delivers 50 horsepower while operating at an 80% efficiency and a 0.85 lagging power factor. Find the total RMS line current. If IB is this and IC is this and VBC is this in a 3-wire ACB circuit, find the reading of a wattmeter connected with its current coil in line A and its potential coil across lines A and B. The plus or minus terminal of the current coil is toward the source and the plus or minus terminal of the potential coil is at line A. A balanced Y load of 50 ohm resistors is connected to a 208 volt ACB 3-wire 3-phase source. Find the reading of a wattmeter connected with its current coil in line B and its potential coil across lines A and C. The plus or minus terminal of the current coil is toward the source, and the plus or minus terminal of the potential coil is at line A. A balanced delta load with impedances of 9 plus J12 ohms is connected to a 480 volt ABC source. Find the readings of a wattmeter connected with its current coil in line A and its potential coil across lines B and C. The plus or minus terminal of the current coil is toward the source, and the plus or minus terminal of the potential coil is at line C. A 600 volt 3-phase circuit has a balanced Y load of this impedance. Find the wattmeter readings for the 2 wattmeter method. A 480 volt ACB circuit has a balanced Y load of this impedance. 2 wattmeters are connected for the 2 wattmeter method with current coils in lines B and C. Find the wattmeter readings. A 600 volt ACB circuit has a balanced delta load of this impedance. 2 wattmeters are connected for the 2 wattmeter method with current coils in lines B and C. Find the wattmeter readings. A balanced Y load is connected to a 208 volt 3-phase source. The 2 wattmeter method is used to measure the average power absorbed by the load. If the wattmeter readings are 8 kilowatt and 4 kilowatt and the Y phase find the Y phase impedance. 2 wattmeters both have readings of 5 kilowatts when connected for the 2 wattmeter method in a 480 volt 3-phase circuit that has a balanced delta load. Find the delta phase impedance. 2 wattmeters are connected for the 2 wattmeter method with current coils in lines A and B of a 208 volt ABC circuit that has a balanced delta load. If the wattmeter readings are 6 kilowatt and negative 3 kilowatt respectively, find the delta phase impedance. 2 wattmeters are connected for 2 wattmeter method with current coils in lines B and C of a 600 volt ABC circuit that has a balanced Y load. Find the Y phase impedance if the 2 wattmeter readings are 3 kilowatts and 10 kilowatts respectively. A 480 volt ACB circuit has an unbalanced delta load consisting of resistors RAC, RBA, and RCB. 2 wattmeters are connected for 2 wattmeter method with current coils in lines A and C. What are the wattmeter readings? For a 4-wire ABC circuit in which VBN is this, find the 4-phasor line currents to a Y load of ZA and ZB and ZC ohms. For an ACB circuit in which VAC equals this, find the phasor line currents to a delta load of ZAC, ZBA, and ZCB ohms. In a 3-wire ACB circuit in which VCB is given, find the phasor line currents to a Y load of ZA, ZB, and ZC ohms. In a 3-wire ACB circuit in which one source line voltage is VBC as given, find the phasor line currents to a Y load of ZA, ZB, and ZC ohms. Find each line has an impedance of 3 plus J4 ohms. In a 3-wire ABC circuit in which one source line voltage is VAB is this, find the phasor line currents to a delta load of ZAB, ZBC, and ZCA ohms. Each line has an impedance of 8 plus J9 ohms. Determine answers that will be printed in the output file when PSpice is run with the following circuit file. And then here we are in the index. Might as well read it, it's not real long. AC for alternating current, AC circuit, AC generator, also known as an alternator, AC PSpice analysis. We've got admittance, conductance of admittance, mutual admittance, self-admittance, acceptance of admittance, admittance diagram, admittance triangle, air core transformer, algebra, complex algebra, alternating current AC, alternating current circuit, alternator, AC generator, ampere, analysis, analysis loop, loop analysis, mesh analysis, nodal analysis, angle, phase, angular frequency, angular velocity, apparent power, associated references, auto transformer, average power, average value of periodic wave, balanced bridge, balanced three-phase load, bridge balance equation, bridge circuit, capacitance comparison, Maxwell bridge circuit, Wheatstone bridge circuit, buffer, capacitance, equivalent capacitance, total capacitance, capacitance, comparison bridge, capacitive circuit, capacitive reactance, capacitor, energy stored, sinusoidal response, cascaded op amps, charge, conservation of charge, electron charge, proton charge, choke, circuit, AC circuit, capacitive circuit, DC circuit, inductive circuit, phasor domain circuit, three-phase circuit, time domain circuit, coefficient of coupling, coil, color code resistor, complex algebra, complex number, angle, conjugate, exponential form, magnitude, polar form, rectangular form, complex plane, complex power, conductance of admittance, equivalent conductance, mutual conductance, self-conductance, total conductance, conductivity, conductor, conjugate, conservation of charge, controlled source, conventional current flow direction, cosine wave, Coulomb, coupled impedance, coupling, coefficient of coupling, Kramer's rule, current, AC current, DC current, current loop, current mesh, current phase, short circuit current, current direction, reference, current division rule, current source, controlled current source, dependent current source, independent current source, Norton current source, cycle, DC direct current, DC circuit, DC P-spice analysis, DC source, delta connection, delta Y transformation, dependent source, P-spice dependent source, derivative, determinant, dielectric constant, digit grouping, direct current, DC, direct current circuit, direction, current direction, dot convention, double subscript notation, drop, voltage drop, joule, effective value, efficiency, electron charge, energy stored by a capacitor, energy stored by an inductor, equivalent circuit, Norton's equivalent circuit, Thevenin's equivalent circuit, equivalent sources, Euler's identity, exponential form of complex number, Faraday's law, ferromagnetic material, flux, flux leakage, magnetic flux, and mutual flux, flux linkage, frequency, angular frequency, radiant frequency, general transformer equation, generator, AC generator, delta connected generator, Y connected generator, giga, ground, grouping of digits, Henry, Hertz, horsepower, ideal transformer, imaginary number, impedance, coupled impedance, equivalent impedance, input impedance, mutual impedance, output impedance, resistance of impedance, reflected impedance, resistance of impedance, self-impedance, Thevenin impedance, and total impedance. Impedance angle, impedance diagram, impedance plane, impedance triangle, independent source, induced voltage, inductance, equivalent inductance, mutual inductance, self-inductance, total inductance, inductive circuit, inductive reactance, inductor, energy stored in an inductor, and sinusoidal response. Inferred zero resistance temperature, input impedance, input resistance, instantaneous current, instantaneous power, instantaneous voltage, insulator, internal resistance, international system of units, inverter, iron core transformer, joule. There's only one word starting with J. Kilo, kilo ohm milliampere method, kilowatt hour, Kirchhoff's laws, Kirchhoff's current law, Kirchhoff's voltage law, Lagging power factor, lattice circuit, leading power factor, leakage flux, line current, line voltage, linear circuit element, linear transformer, load, balanced load, delta connected load, parallel three-phase load, unbalanced load, Y-connected load, long time, loop analysis, loop current, magnetic flux, matching, resistance matching, maximum power transfer theorem, Maxwell bridge, mega, mesh analysis, mesh current, MHO, Mo. Oh, that's like a Siemens, isn't it? Micro, milli, Millman's theorem, model, op-amp model, P-Spice op-amp model, model transformer model, mutual admittance, mutual conductance, mutual flux, mutual impedance, mutual inductance, mutual resistance, nano, negative charge, negative phase sequence, network, C circuit, network theorem, C theorem, neutral, neutron, Newton, nodal analysis, node, reference node, node voltage, nominal value of resistance, non-inverting voltage amplifier, Norton's theorem, Ohm's law, op-amp, see operational amplifier, open circuit voltage, operational amplifier, op-amp, op-amp model, open loop voltage gain, P-Spice model, operational amplifier circuits, buffer, cascaded op-amps, inverter, non-inverting voltage amplifier, voltage follower, voltage to current converter, oscillator, output impedance, output resistance, parallel connection, passive sign convention, period, periodic quantity, effective value, permeability, permittivity, phase angle, phase current, phase difference, phase relation, phase sequence, phase voltage, phasor diagram, phasor domain circuit, pico, plane, complex plane, polar form of complex number, polarity, reference voltage polarity, voltage polarity, positive charge, positive phase sequence, potential drop, potential rise, power, apparent power, average power, complex power, instantaneous power, maximum transfer of power, reactive power, real power, resistor power, three-phase power, power factor, lagging power factor, leading power factor angle, power factor correction, power measurement, single phase power measurement, three-phase power measurement, 2 wattmeter method, power triangle, primary winding, probe, proton, P-Spice analysis, AC P-Spice analysis, DC P-Spice analysis, probe P-Spice analysis, transient analysis, three-phase circuit analysis, and transformer circuit analysis. Radian frequency, rationalizing, RC time constant, RC timer, reactance, capacitive reactance, reactance of impedance, and inductive reactance. Reactive factor, reactive power, real number, rectangular form of complex number, reference current direction, reference node, reference voltage polarity, references, associated references, reflected impedance, relative permeability, relative permittivity, resistance, equivalent resistance, resistance of impedance, resistance, input resistance, internal resistance, mutual resistance, nominal resistance, nominal value, output resistance, self-resistance, Thevenin resistance, tolerance, total resistance, resistance matching, resistivity, resistor color code, linear resistor, nonlinear resistor, sinusoidal response, resonance, frequency, right-hand rule, rise, voltage rise, RL time constant, RMS root mean square value, secondary winding, self-admittance, self-conductance, self-impedance, self-inductance, self-resistance, semiconductor, series connection, short circuit current, SI, International System of Units, Siemens, sine wave, sinusoid, average value, effective value, source, AC source, controlled source, current source, DC source, dependent source, equivalent source, independent source, Norton source, practical source, Thevenin source, and voltage source. Source transformation, SPICE program, step-down transformer, step-up transformer, subscript notation, current subscript notation, voltage subscript notation, superposition theorem, susceptance, temperature coefficient of resistance, Terra theorem, maximum power transfer theorem, Millman's theorem, Norton's theorem, superposition theorem, Thevenin's theorem, three-phase circuits, balanced three-phase circuits, P-SPICE analysis, unbalanced three-phase circuits, three-phase power measurement, time constant, RC time constant, RL time constant, time domain circuit, time varying voltages and currents, timer, RC timer, tolerance, resistance tolerance, transformation, delta Y transformation, source transformation, transformation ratio, transformers, air core transformers, ideal transformers, iron core transformers, linear transformers, P-SPICE models of transformers, step-down transformers, step-up transformers, transient P-SPICE analysis, turns ratio, 2 watt-meter method, unbalanced three-phase circuit, unit symbol, units, SI units, VAR, voltage, induced voltage, node voltage, open circuit voltage, phase voltage, voltage difference, voltage division rule, voltage drop, voltage follower, voltage polarity, reference voltage polarity, voltage rise, voltage source, controlled voltage source, dependent voltage source, independent voltage source, Thevenin voltage source, voltage to current converter, volt ampere reactive, watt meter, Weber, Wheatstone bridge, winding, primary winding, secondary winding, work, Y connection, Y delta transformation. And that's it. Up to this. What's this got to say? Shawm's interactive outline series. Shawm's outlines and MathCAD combine, the ultimate solution, now available, electronic interactive versions of engineering titles from the Shawm's outline series, electric circuits, electromagnetics, feedback and control systems, thermodynamics for beginners, fluid mechanics and hydraulics. McGraw-Hill has joined with MathSoft, makers of MathCAD, the world's leading technical calculation software, to offer you interactive versions of popular engineering titles from the Shawm's Outline series. Designed for students, educators, and technical professionals, the interactive outlines provide comprehensive on-screen access to theory and approximately 100 representative solved problems. Hyperlinked cross-references with an electronic search feature make it easy to find related topics. In each electric outline, you will find all related text, diagrams, and equations for a particular solved problem together on your computer screen. Every number, formula, and graph is interactive, allowing you to easily experiment with the problem parameters or adapt the problem to solve related problems. The interactive outline does all the calculating, graphing, and unit analysis for you. These live interactive outlines are designed to help you learn the subject matter and gain a more complete, more intuitive understanding of the concepts underlying the problems. They make your problem solving easier with power to quickly do a wide range of technical calculations. All the formulas needed to solve the problem appear in real math notation and use MathCAD's wide range of built-in functions, units, and graphing features. This interactive format should make learning the subject matter easier, more effective, and even fun. For more information about Shawm's interactive outlines listed above and other titles in the series, please contact Shawm Division, McGraw-Hill Inc., 1221 Avenue of the Americas, New York, New York, 10020, with the phone number 1-800 3383987. To place an order, please mail the coupon below to the above address or call the 800 number. Okay. So going to give you a price. Software requires 386 or 486 PC or compatibles with Windows 3.1 or higher, 4 megabytes of RAM, 4 megabytes of hard disk space, and 3.5-inch disk drives. Oh, there we go. It's $25 each. Or you can get software and printed outline. Costs more. And this is feedback and control systems, electric circuits, electromagnetics, fluid mechanics and hydraulics, thermodynamics for engineers. Wow. I imagine this is all well and truly out of date. It talks about 386 or 486. So this is from like the early 90s. This is the second edition, but anyway. Oh, here we go. Free software. Oh, no, they're not talking about free as in, yeah, they mean free as in beer. PSpice is a circuit simulator software package used to calculate the behavior of electrical circuits. Class instructors can receive complimentary evaluation versions for both the IBM PC and Macintosh by submitting a request on company or educational letterhead to this address. Duplication of the diskettes for your students is encouraged. Yeah, there you go. So we made it. I'll throw over the farewell cam. We'll wrap up.
And that's a wrap. So that was a bit of fun, wasn't it? There's a lot in there to learn. It would take a long time to do all of those calculations. And I have to say, some of it there at the end, it was beyond my pay grade. I don't know much about three-phase power systems and apparent power and all this sort of stuff. So yeah, maybe I'll learn more about that as time goes by. But I really just want to keep up with the learning the art of electronics course. So I'll do whatever it covers. But some of that stuff was power electronics, which really isn't part of the syllabus for the learning the art of electronics stuff. So, but some of the earlier stuff, certainly the Thevenin equivalents and the Norton equivalents and that sort of thing, that is definitely being covered in the course. Anyway, that's the end of this video. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.